3, 2, 1. All right, let's see. I think we're live. I think that's it. Welcome everyone to tonight's AP Physics C E&M CRAM finale. It's great to have you here. I am excited to go through, well, all of E&M in this 5-hour period. Super excited. For those of you who don't know me, my name is Peter Apps. I have been teaching physics for going on 15 years. AP 1C, all the flavors and stuff like that. So we're going to buckle up and have some great time together, kind of going through the nuts and bolts of the test and the content from now until, well, 5 hours from now, 10 o'clock my time. I'm not sure about your time. Hopefully it's earlier, but either way, welcome to everybody who's also just come from Sam's APC MEC final. Hope you got a lot out of that final as well. And yeah, let's dive in and get going here. All right, so let's see, I can share this like that. I think that's working. All right, cool. All right, so just in case you didn't know, we're recording this. We're going to be playing this back for all the CRAM finales for the later, what's the term? Exam dates, we'll call it that. Administrations, that's the date. So if you ask a question or I may call you out in a comment or stuff like that you're going to post, your name may show up. So if you don't want it to, change your name to something that's not going to show up because that's the way this works on there. All right, cool. I'm going to skip this for a second. I'm going to skip this for a second. Come on. Let's go to the next slide. Go. There you go. And don't forget to check out all our socials at ThinkFiveable. I'm skipping Amanda's welcome because she will be joining us in approximately a few minutes, give or take. So yeah, she'll jump in and say hi to us in a little bit. So let me go over kind of the rough overview of what we're doing. Obviously, these times may change a little bit depending on the questions you guys ask and just how long it takes us to get through stuff. But this is the game plan. From now until roughly 6:30 my time. So hour 0 to hour 1.5, we're going to be doing electrostatics and Gauss's law. Then we'll do a little bit on capacitors and dielectrics, round that out with some circuits, and then finally the last chunk will be magnetic fields, Ampere's law, Faraday's law, electromagnetic induction, and then if we've got time, some more FRQ practice. So that's all coming up in there. Okay, let's see if this works. Okay, cool. And I'm going to hold off on this for a second because I'm going to have Amanda come in and do her little shindig.
What's up, everyone? I'm so excited to be here live for this AP Physics live stream. I wanted to, stop in and say hey and let you know that I'm thinking about you today. I'm thinking about you tomorrow, too, during your exam. And really wanted to just, make sure you know that we're out here. So I have a couple of things for you. One, if you need any help during the stream, we have TAs that are going to be swarming the discussion threads below. So make sure you post any content questions for them because I know there's going to be a lot of students coming in throughout the stream. And Peter's going to be kind of chugging through and really making sure that he covers all the content. So just post your question in the discussion thread and it will get answered. If you have any tech issues or any questions about the stream itself in that sense, then you can chat with us on our bot on the bottom and our success team will support you there. So the discussion thread is just for content or anything, help with the exam specifically. The chat is for any tech issues or anything like that. More fun, the other thing I wanted to remind you of is the social contest that we're running. So we did this last year as well, and things are moving this year. So what we're doing is one student every single day will win $100, which basically pays for your AP exam from our social media contest. So how do you play? All you need to do is post on any social network. You can do TikTok, Instagram, Twitter, something about your AP experience, something that is kind of calling out the nonsense of College Board, what it feels like to study after a year of remote learning, showing your study space, anything about your experience, what it's like to be in this 5-hour cram. Make sure that you include Fiveable in some way in the caption or something, and then you tag with Fiveable and Yes We Cram, and tag us in it too, so that our social media judges, which are all students, can decide on the winner. And they're going to decide based on a couple of things. One, like, does it have the most likes? That's going to help you win. And do they see it? And are they thinking like, that is so fair. That's exactly what this feels like. Feels really relatable. So make sure you get your submissions in. We're going to be running that throughout all 3 administrations. You can play anytime. You can submit as many different things as you'd like, and one student will win every day. So I'm really excited to watch what you guys post. I can't wait to see it. I'm going to kick it back over to Peter. If you need me for anything, I'll also be in our Discord channel throughout the night. My DMs are always open. But like I said, post your content questions in the discussion thread. Chat are on the chat bot here if you need any tech support. And you got this. You totally got this. You've made it through this far in this crazy year. You totally got this. Don't worry too much about your exam score. Peter's going to help you out with all the concepts you need. So I will see you later, and I'll let Peter take it from here. See you guys around.
Thanks, Amanda, for the contest. Post on social, do all that awesome stuff. So now let's dive into the CRAM. All right, so I need to turn on captions here. There we go. So if you could, first off, anytime you have a question, Q&A, right below this window, there should be a box for you to start putting some questions in. You can upvote the ones that you definitely want to get an answer on. You can post, just scan them before you post a question, just to make sure it's not a triplicate or quintuplet of those questions. And they will get answered by our wonderful TA, Danny. And I will also look through there when we get to breaks and stuff like that and kind of pull some important questions up. So if you have Q&As right below, stuff like that. But right now, I would love for you guys to jump on menti.com and use this code 34847492. And I just want to see how we're feeling today. What's your impressions? Bad, stressed, see above, happy, bad, sad. Wow. There's some stuff here. Okay. So there's quite a lot of exhaustion going on, and I totally get that. There's a lot of some of that crazy College Board just stress here, and I understand. It's been a long year. You guys have put a lot into this course, whether you're self-studying or doing it with your own teacher, and it can be a little stressed out, a little crazy here. Happy, okay, stressed. Hey, some random text. That's kind of fun. All the stuff going in here. Okay, stress seems to be the big one. So let's deal with some stress right now. Okay, procrastinated. Yes, exhausted. I understand. Hopeful. I like that one. All right, cool. So we'll come back to that in a second here. As we keep going through. Bad teacher. Oh no. We'll do our best to get through some of that stuff. So we will hopefully by the end of this, these negative feelings will be at least a little bit reduced. All right, so let's do this first. And I'm going to stop sharing for a second here. All right. So right now, stop for a second. Take a breath. Okay, take a deep breath. We're going to be fine. Okay, number one rule, the exam does not determine your worth. Okay, whether you're a 3 student, a 5 student, a 1 student, it doesn't matter. It doesn't change on who you are. Okay, set your goals, obviously. I'd love for all you guys to get 5s, but this does not dictate or determine anything about who you are as a person. Okay, and to be honest, I've had kids get 5s on this exam and then go into physics and say, wow, this was easy. I've had kids who've gotten 1 on this exam and gone in and said, wow, this was easy for their freshman year physics. Whether you opt out of the class or not, whether you get a great score or not, it's a learning step. It's a first step in a process. And please don't think that tomorrow's exam is the end of your journey as a learner, as a physicist, whatever. Keep working and learn from it. Okay, so there's my little side talk for that. All right, back to the screen. Let's dive in here. All right, so let's go. Next slide. All right, so let's talk exam. First off, some of you are taking the exam tomorrow. Okay, that will be the traditional style exam. Some of you guys are taking this also in late May. Again, traditional style exam. And some of you are taking it in, well, mid-June, which will be the digital only exam. And that digital only exam will be the one that is slightly different here. So we've got, for everybody, section 1, 35 multiple choice questions in 45 minutes. That's half of your exam score. Okay. Second one, section 2, free responses, 3 questions, 45 minutes, half of your exam score. If you're a June person, well, then all your stuff is multiple choice. All right. So I'm going to just preface this by saying we've got, if you're a June person, we will be doing multiple choice questions and free responses, because we are tailoring this more towards the early May people right now. June people, a lot of the questions that will show up on the free response could also be very easily turned into multiple choice. So keep working through those free response questions with us. Even though they're free response and they won't be on the June exam, they're still going to be important for working through this process. All right. Let's turn that back on. Okay. Next part. So what's going to be on the test? These are the rough percentages from the CED. That all may change in, a year or so. But for right now, this is what we're sitting at. Electrostatics, Unit 1, charges, Coulomb's law, stuff like that, makes up somewhere between 1/4 and 1/3 of the exam. Okay? We're going to spend a good chunk of time on Unit 1. Unit 2, conductors, capacitors, dielectrics, not so much. That's like 10% of the exam, or 15% of the exam. Electric circuits is somewhere between around 20%. Same deal with magnetic fields, and then electromagnetism makes up the last percentage. Out of those, typically, you're going to see a lot of multiple choice questions for all the units, but free responses tend to be clustered with Unit 1, Unit 3, and Unit 5. Historically, you can find ones on other ones, but typically you're going to see an electrostatics free response question, a circuits free response question, and an electromagnetism free response question as well. Okay, now the question my students always ask me, and I figured we'll be really upfront about it. What do I need to score a insert grade here? So the good news, I guess, is that you don't need to get 90% to get a 5. You don't even need to get 80% to get a 5. A 5 historically on this exam is about 61% of the points, give or take. It's going to vary a little bit depending on the year, but in general, if you can pass the exam, if this was a paper and pencil test I gave you in my classroom, if you pass it, you're going to get a 5. If you get just under half the points right, that'll be a 4, and about 1/3 of the points right puts it at a 3. Okay. Why are we going over this part? Well, number one, it's the stress part here. We don't need to worry about getting every single question right. Again, awesome. Be that 1 or 2 people that gets a perfect score. Go for it. But also, don't stress yourself out. If there is a question, a multiple choice question, you say, I really just don't know. Bubble in an answer and move on. It's okay. Same deal with the free response part. If there's a free response question that is just, this is not making sense to me, okay. Get the points you can out of it. Move on and nail the other 2, and you'll be in decent shape. So there's my advice. Don't stress out about every single little point. Get the ones you can, guess on the ones you don't know. And again, just over 50% puts you in a 4 to 5 range. It's not a bad percentage to be at. All right. When we look through these, there will be several task words. And again, if you're coming from Sam's EMEC session, she did basically the same sort of thing. I'm going to highlight these quickly, simply because I'm kind of assuming, for right or for wrong, you've already gone through the other Physics C classes on them. So calculate means do math. Specifically, do math and get a number on there. So properly substituted numbers, labeling of units, and significant figures. Actually, I have a laser pointer. There we go. So calculate, we're looking for number stuff. Compare, how are they the same? How are they different? Derive. Derive is one of these that we're going to see a lot. This typically means start with a basic fundamental law, Coulomb's law, Gauss's law, Ampere's law, Faraday's law, and do something with it to come up with a correct answer mathematically. Most of the time, derive will be done symbolically. We won't put numbers in, and we'll come up with a usually calculus-based answer because we are physics C. Describe simply means just tell me about it. Determine, make a decision, or arrive after reasoning, observing, or applying mathematical routines. All right, so determine could mean here's the answer because ... Here's the answer math, or here's the answer observations from a paragraph. Kind of got all those options here. Explain, I'm skipping estimate because that one simply just says round your answers-ish. Do a little bit of rough math, mental math. On here, explain really wants the why. This is the how does this work and why does this work. Two keywords in here that are going to show up in every explain question, and you've got to make sure we answer that part. All right, so explain versus describe. Describe just tells me how it's going to be. The current flows in a counterclockwise direction. Okay, great. Explain the current flows in a counterclockwise direction because of the applied magnetic field. All right, justify means explain but provide evidence and reasoning. So go beyond the why. Let's get some CER type, or if you took Physics 1 last year, the BCDA method, basic physics, cite evidence, draw it all together, answer the question. Explain but deeper. Prove it to me. Label, plot. Okay, plot versus sketch. I think we'll draw a big distinction with. Plot means we care about units, we care about sizes, we care about dimensions. So it's points on a graph and connecting them. Sketch just means what's the general shape? Is this a concave up? Is this concave down? Is this logarithmic? Is this exponential? State, indicate, circle. Well, that's kind of just check the box or circle the right answer, I guess. Really don't worry about explaining it. Do not elaborate. Do not explain. Check the box, greater than, less than, equal to. And finally, verify. Verify means, does this match the hypothesis? Does this match the scientific theory? Often combined with why. But verify would mean something like, hey, Ohm's law says that voltage and current should have a linear relationship. When I plot them, or when the students plot them, or when the lab plots them, it's a linear fit, so Ohm's law applies. If it wasn't a linear fit, it doesn't apply. That's verify. Okay, so that was multiple choice and kind of those task words and stuff like that. Free response tips. I'm hitting them now just so in case we run out of time later, we can have them right now. Number one, know the equation sheet. I'm not saying you have to memorize all of the equation sheet. Okay, it's great to memorize the ones that you're going to use the most. Memorize Ohm's law. Memorize Gauss's law. Memorize Coulomb's law. But also know where on that sheet are the given things. We start off with charges. Then we go to Gauss's law. Then we go to circuits. Then we go to magnetism. Then you go to EMI. Know the rough spots on that sheet where you can find the equations and find the numbers. So even if you're not sure, I think Gauss's law involves Q somehow, go look it up, but know roughly where in that sheet it's going to be. That way you're not eating up a ton of time just skimming through the entire reference table saying, hey, this is where I think there's an equation. Know roughly. Okay. When you're doing free responses, skim the whole section first. Okay. Go through all three questions. And maybe you're a circuit person. Circuits is my favorite topic. I will always start with a circuit question on the FRQs. Even if the other ones have nothing to do and I'm not sure about it, I'll always start with the circuit one because that's my jam. That's where I will be confident about getting the best answers and the easiest answers and stuff like that. Start with the confident one first. Then go to your second confident and then hit the third one. Okay. you've got 45 minutes to do 3 questions, which means each question should ideally take you about 15 minutes. When we do them here, coming up, we will spend roughly 2 minutes per part, which for a generic question will put you somewhere in that 12 to 15 minute range on there. Okay. Show your work. This one's bolded in big because that's really it. I've graded exams before for AP, and it is really, really important that you make it clear what your thought process is. Show your work, because even if you make a little math mistake, if you show me the process to get there, I can give you points for the process of getting there. Instead of not showing your work, just putting down an answer and then it's wrong and you get nothing for it. Show your work from step 1 all the way down. That way we're going to be clear about getting the maximum points we can. Because as we'll see, some of the points you get are simply for writing down Coulomb's law, or writing down Gauss's law, or writing down that the area of a circle is pi r squared. Yeah, that's right. Sort of stuff. Okay, know your task words. We went over them already, but don't do more than you have to do. If they're asking you to sketch something, you don't need to plot every point. If they're asking you to explain, don't go into justify. If they're asking you simply just to calculate, you don't need to drive it all. Just put the numbers in and get the answer. Okay, and what I do, especially if you're taking this paper and pencil, is keep a list. Keep a running list on the side of what information you're given. Are you given currents, charges, areas, anything like that? Just make a list. That way you can also use your list to guide you to the equation that would work. Okay, if we're talking about voltage and current, I'm kind of leading towards the circuit chunk on there. Maybe if I'm resistance or power or stuff like that. But if I'm given voltage and charge, maybe I'm looking for work or energy or capacitance, depending on there. So keep a list, and that list can help you get through. I kind of already mentioned this one already, but there is partial credit. Write down stuff. Even if you have no clue, guess at something. I think this equation makes sense for this problem. Great, jot it down. Same deal with graphs. If you're given a graph, always, always, always write down something on there. Even if you have no idea what the graph should look like, do something that you think makes sense. Draw an exponential, draw a logarithmic, make it a straight line. I don't care, but don't leave it blank. Blank is the right word there. Don't leave it blank, please. Because as we'll see, graphs are a ton of points that we can leave on the table. So please don't. Next one, put units in your answers, please. Sometimes the scoring guidelines say you need a unit. Sometimes they don't care about it as much. You won't know that in the test. Always, always, always put units with your answers. Use dimensions to your advantage. So if you know the units are supposed to be this and you're trying to work through, we've got options here. Leave the algebra heavy answers for last. We also say leave the calculus heavy answers for last. If it's asking you to derive a calculus equation, that's probably only worth 1, maybe 2 points. We can probably put that off to the side a bit, do the easy low-hanging fruit first, then come back to that one. Components on FBDs, that one we're probably not going to see very much, but I could say if you're doing stuff with vectors, don't overdo it. Please write legibly and telegraph your answers. Make them super obvious. Put your final answer in a box. Circle it. Draw an arrow saying, this is my answer. When we're grading hundreds of papers a day or thousands of papers a day. Make it clear to the reader what your final answer is. They will thank you for it, even though they'll never know you in there. All right. So that's the exam in a nutshell. Let's pause for a second here. Again, gather our thoughts. We're going to dive into the content. Big thing is, you got this. Okay. Even if you're a person who self-studied for this whole time, you had the best teacher in the world, you had the worst teacher in the world. You are here right now putting in the time, putting in the effort to get a great grade on this exam. Okay. The fact that you're here watching this puts you well above every kid who's not, because they're not putting in the time or the effort. You are. So let's go with this. And without further ado, let's dive into electrostatics. All right, so I'm going to hit the basics here. We got not much of the basics, but some of the basics here. charges. Pretty straightforward, pretty simple. If we don't know this, we might have an issue for the stream. But we've got protons, neutrons, electrons. Plus 1e, minus 1e, 0e. Great. Likes repel, opposites attract. We've probably heard that saying since, for my students, it's at least 4th grade, 8th grade, 10th grade, 11th and 12th, I think is what we do for ours. But likes repel, opposites attract. So if they are the same charge, they're going to repel. If they're opposite charges, they're attracting. And here's the caveat we might not be sure about, but a neutral object will always be attracted to a charged object. That's how the balloon can stick on the wall, because the balloon sticks on the wall by attracting whatever the opposite charge is in the wall and repelling the same charge. That's how that works. We also see the repulsion. Look at the kid's hair. We've got all the spikies standing up far away because they are all the same charge, and they want to get as far away as possible from each other. All right, so how do we get a charge? There's 3 main ways. Okay, there is friction. Simple, you rub 2 things together. Balloon and hair is a great example. The balloon will gain the electrons. Your hair will lose the electrons. Rubber and silk does the same sort of thing. One object gains, the other object loses. That's charging because of friction. If you're a chem person, it has to do with electronegativity and affinity for electrons and stuff like that. We really don't care. We care about the fact that one's positive, one's negative. All right, second way is contact. Touching a charged object to another charged object makes charges go evenly between them. So equally charged. A better way of saying this probably is that they have the same electric potential. So they will end up with the same potential on there. If they are exactly the same size, they will end up with exactly the same size and the same material will end up with exactly the same charge. If they are different sizes, obviously the larger one holds more charge and the smaller one holds less charge. But they will do that until the potentials are equal, and then they will not have charge flow back and forth between them. In induction, you bring a charged object near an charged object, you're getting the charges aligning, like in this example here. I bring a negative object towards the sphere. All the positives in the sphere rush over to it, and the negatives get pushed away. If I happen to connect this to ground or give those negative charges a place to go, they will continue to book away and go further and further and further away. Then if we cut the cord, cut the wire, we will be left with a positively charged sphere. Okay, so induction will charge the opposite polarity of whatever object you're bringing close. Contact will charge the same polarity as whatever you are touching together. Okay, so touch, they get the same charge. Bring close, you can make it the opposite charge. Okay, and just to point out the law of conservation of charge. One of our fundamental laws in physics, the total charge in an isolated system must remain constant. So if I am causing charges to flow from one part to another, if I look at the entire system, both objects, the total charge must stay the same. Every electron that goes from sphere A to sphere B must be accounted for. We can't simply just ignore charge or stuff like that. Now, if we run into a case where we are tying something into ground, well, this ground is maybe it's part of my system, maybe it's not. But if I count the sphere and the rod as part of my system, then I could say, hey, charge left, it moved. But when we're talking about an isolated system, the charge must remain constant. Total charge doesn't change. Okay? And this will be important too when we talk about circuits. This leads into things like Kirchhoff's voltage law and other parts like that. All right, math time. Coulomb's law, probably the most important law for electrostatics. This simply says everything we've kind of come up with before here. Like charges repel, opposite charges attract, and the charge force between them is equal to K Q1 Q2 over R squared. Now, there was a question on Fireball a little bit earlier. Do we use K? Do we use 1 over 4 pi epsilon naught? As a grader, it doesn't matter. We're smart enough to know that K is 1 over 4 pi epsilon naught. But there might be cases where it's easier to cancel something out in the charges or in the radius if we write it in the long form. So by all means, feel free to write it as K for while you're doing your workout. And when you get to your answer, maybe it's worth checking. Is 1 over 4 pi epsilon naught a little bit better form to finish it? Maybe something cancels out or makes it nicer in there. Okay. All right, so it is time for your first practice question. All right, so I'm going to open this poll. We'll see if that works. And I'm going to give you guys a minute to solve this question. Minute is roughly the right amount of time for a multiple choice question. So we will work through this for a minute. Go ahead and answer in the poll, which should be popping up. Hopefully it is. We'll see if that works or not. And we'll go over it in, well, 47 seconds from now. Five, 4, 3, 2, 1, and done. Okay, let's see how we did. Can I publish the results? And show them? Can we see? All right, so the correct response here is A, and 90% of you guys said A. Great, great, great job. Let's talk about why. Okay, so first off, A is the correct answer here. Let me hide the poll. Don't need that anymore. All 3 charges are positive, plus Q, plus Q, plus Q, which means they're going to repel each other. We're not getting any sort of attractions going on. Newton's second law, remember him from Physics 1 and Physics CMEC, says that the acceleration is proportional to the force on the sphere. So we are looking at the sphere on the right. This guy right here is going to experience a force, and that's proportional. That will tell us the acceleration. And Coulomb's law says that the farther away you get, the force will decrease. So these 2 charges on the left are going to be repelling our charge on the right, and that will get weaker as that charge moves farther away. So choice A is the correct answer here. So to move to the right, with the acceleration starts off really big, and the farther this gets away is going to be slower, less and less and less as we go down. All right, cool. Question 1 done. Next one, talking about conductors and insulators. When we talk about charge can grab on and be held by many different types of materials. And they're also going to do this a little bit differently. A conductor, typically metal, but doesn't have to be metal, is a material that allows charge to move freely through it from one side to the other, moving through. Think of like a wire. The charge goes through pretty easily. An insulator is a material that tends to hold on to charge in a fixed location. So wherever the charge gets put into our insulator, it will stay there. It will not be able to spread out and move around. Okay? And we can see that in the pictures. The conductor is going to have, if I put a positive charge on this conductor, all those positive charges move around, and notice that they are repelled by each other. They're going to spread out as much as they can to the outside. So they are as far away from each other as possible. This becomes really important because we'll see in a little bit. The inside of the conductor may not have any charge on it. It may not have an electric field going on in there. Compare that with an insulator. We put a negative charge, in this case, on the insulator, and that negative charge takes up the entirety of that insulator, fully filling it on there. So on an insulator, the charge is distributed throughout the entire thing. For the conductor, it's really only on the surface of the conductor. Okay? And that is a big distinction between the two. Got to remember that. Conductors hold their charge on the outside, whereas insulators hold their charge all the way throughout. And again, this is showing positive and negative. It doesn't matter whether it was a positive charge or a negative charge. The pictures are going to be pretty much the same. Conductors on the outside, insulators all the way throughout. All right, so that is Coulomb's law and charge in there. talk about likes repel, opposites attract, and we can also visualize that through electric fields. Okay, so electric fields are similar to gravitational fields. They are showing which way an object would travel if it's placed between them. Now, electric fields are always drawn so that the positive charge is showing what's moved. So the positive charge is going to get pushed away from a positive and drawn towards a negative. So all the arrows are always showing the direction of a positive test charge. And the shapes are hopefully familiar. We've got the curving arches between the positives and negatives. We've got the hyperbolic sort of shape between the two positives. And I suppose if these were two negatives, we'd see the same exact shape, just with the arrows flipped, with them all pointing towards the center or towards the negative charges, if this was flipped around. We also have we have a negative sheet of material and a positive charge by it. We're going to have all these things be bending towards it and sticking to it. Basically, the same half of number one, just replace that negative charge with a negative sheet. And another big one here is if we have two parallel plates, one positive, one negative, the field between them is horizontal or parallel lines going from the positive plate to the negative plate. Okay. I'm sure you guys also have mentioned or heard about at some point in time the field strength. How strong is the field? Well, if we're given a picture, we can make a guess based on how closely the lines are together. So, for example, in this case right here next to this positive test charge, the field is pretty strong. If I move out to the center here between the two charges, the field is basically nothing. And if I get it perfectly in the center, it is 0 because there's no electric field line that will go through this point. Okay? So the density of the lines around our point gives us a proxy for talking about how strong the field is. With the parallel plates, notice how all these lines are equally spaced, and there's no spot where the lines get closer or farther away from each other. That means that inside these two parallel plates, the field is exactly the same strength everywhere. It doesn't matter whether I'm right by the positive plate, right by the negative plate, I will experience the exact same electric field everywhere between these two plates. Okay. Now, that doesn't hold true at the ends, but if we assume these are infinitely long, which a lot of your free response questions and multiple choice questions will do, the field will be identical all the way through. All right. Next chunk, electric fields and conductors. We kind of mentioned this already, right? If we take a conductor, in this case, a metal ball, and we put it between two parallel plates, we will see the following thing happen. The positive side will cause the negative charges in the sphere to be attracted to it, and therefore the left-hand side of the sphere becomes negative. The right-hand side will become positive, repelled by the positives, attracted by those negatives, and we're getting the field lines go away from the positive towards the negative, and we're bending in here because the field lines must touch that metal cylinder at a 90-degree angle. They must be perpendicular to the surface. Then we get the opposite thing happening on the other side. The field lines leave at a 90 and then travel over to the negative plate. Okay, now this one's a solid cylinder. So we are looking at this not being hollow, but if we were, it really doesn't change a ton. Yes, there's a hollow part in here, but there is no electric field inside this cavity. All the field is on the surface of the conductor. Inside, there's nothing there. Okay. And then one more picture just to make it clear. If we get one where we are enclosing some charge, like a positive charge, inside a loop or a cylinder of a conductor, we get the same basic idea. The positive here, field lines go away from it. They must meet at a negative on the surface, in this case, the inner surface of our object, and then positives on the outside, because they were repelled, continue those field lines outwards. Inside the conductor, there is no electric field. I don't know how much more explicit I can say that, but inside a conductor, there is no electric field. It is just on the surface of the conductor that we will see an E field happening. All right, so E field. How do we calculate it? Here's our equation. Electric field strength represented by an E. It is a vector, which means direction matters. Okay, positives and negatives mean something. It means which direction are those arrows traveling. It is equal to the force a test charge experiences. So electrostatic force, Coulomb's law over Q. If we plug in Coulomb's law here as KQQ over R squared, one of the Q's cancels out. So we can simplify it to simply just KQ over R squared, where Q is the big charge we care about. So Q, for example, would be the charge in the center of this ring, not the test charge. And again, we can also sub out 1 over 4 pi epsilon naught for K. Both these two are pretty much equivalent to each other. It's your preference which one you use. Your reference tables give you the longer one. So that is your choice. But again, if this is a derived question, you can write K and be perfectly fine with that. All right. Question to practice number 2. Let's start the clock, open this poll, and work our way through this one. All right, 12, 11, 10. Keep ticking down. 5, 4, 3, 2, 1. All right, let's see how we did. Publish those results, show those results. And we get the correct answer is A. And 100% of you chose A. Great job. Great, great, great. Now, I'm not sure if this was me. I'm not sure if I chose A because it's the right answer or because I didn't feel like doing the math to figure out what the heck B, C, and D are all trying to tell me. But either way, A is the right answer here. So let's talk about it a little bit. All these 6 positive charges are held fixed. They are immovable in here, and they're equally spaced around the circumference of the circle. That's the key part. Because they're equally spaced, they will each try to exert a force away from them towards the center of the circle. So our point here right in the middle will experience a force that is equal in every single direction. And according to Newton's laws, if I have a force that is equal in every single direction, that means the net force is 0. There is no force. It's perfectly balanced. There's no unbalanced force there, which means we will not have an electric field in that location. Okay. If you're wondering, B, C, and D, those all come from doing some trig to figure out how much of a force it is from one particle and work your way through. So they're plugging it into that electric field equation on your reference tables. But because of symmetry, we get to kind of ignore all that and just jump right to A. So great job choosing that one, whether it was a guess or not. Either way, good job. All right. So that is electric field. Again, we'll come back to a lot of this stuff in a bit. We're just laying the groundwork right now. The next part is electric potential difference, otherwise known as potential difference or voltage. I really like using potential difference as the term right now. We'll sub it for voltage later on, but potential difference. It is the difference in the potential or the energy-ish, not quite energy, but close enough for right now, to move between 2 points in an electric field. All right, it gets the symbol V, hence voltage. It's measured in volts, voltage, but it is defined as work divided by charge. Now, if I remember from physics C or mech of some kind, work is force times distance, or force dotted with distance if you were a calc student in there, meaning it must be a parallel path between those things. So, for example, if I am moving from, let's say, this middle ring inward, it will take some work to shove a charge towards the charge in the center. And that work must be equal to KQQ over R squared. the Coulomb's law times the distance I actually push it, which in our case is going to be a radius because we're changing the distance that we have between the two, which simply is KQ over R. Now, if we have several point charges that I want to move, I can, well, simply say, okay, so the total potential difference is K, because it's a constant, times the sum. How much work did it take to move every single one of them? Add them all up, that gives me the voltage going on there. So on your reference tables, and really one charge, many charges, same basic equation through there. Okay. We can also find voltage if we know the electric field strength. Now, so the previous one, I was assuming that we knew a charge. We knew how big the charge in the center was, but that may not be the case. We may be given, here's the electric field, move it from point A to point B. How much work is that going to do? Well, if I go through this, FE over Q, electrostatic force over Q, we saw that earlier. That's the electric field strength. And electric field strength dotted with D, because again, we care about parallel parts here, is the voltage. And that gives us the integral form for this. So the change in voltage between two parts is the negative integral of E dot dr. Again, dot product. We care about the parallel components of E and R for this. And then the negative, you may say, well, why are we having a negative sign? That's because the closer we get, the farther we get, the more negative the voltage becomes. And the closer we get to the charge, the more positive the voltage becomes. Go back to my picture here for a second. If we're imagining trying to get a test charge near Q, if I'm pushing a positive charge near it, it's getting harder and harder and harder and harder and harder. I've got to give it more and more and more work to get that closer, which is why we're talking about positive. If we're going the opposite direction, the particle kind of wants to go there already. So we're going to go with a negative in that case because we are taking energy away from that particle to put it in a mechanics sort of frame. Your reference table also has the derivative form of this. So whether you choose to do integral form or derivative form is going to depend on the question. They are the same exact thing. Notice they both have the negative sign there, which tells us that V will decrease as R increases. I should point out also, potential difference is a scalar quantity. It's a dot product, which gives us the scalar form of this. So V doesn't have a direction. This simply just says, am I increasing or decreasing the potential difference between those 2 points? Okay, so don't think of the negative as having a direction. The negative just tells me increasing or decreasing because V is a scalar, not a vector going through there. All right, and the final part here is potential energy from an electric field. Doing the same sort of thing, V equals W over Q. Work could be changing the potential energy. That is a perfectly fine definition of that. So we can talk about potential energy as the amount of potential difference done or times the charge. The way I like to think about this one is in the context of a battery. If I take a loop of wire and connect the positive and negative terminals on a battery, that battery, let's say, is 1.5 volts. That means I'm giving 1.5 joules to every coulomb of charge, or 1.5 electron volts to every electron that goes through that circuit. I'm giving a certain energy to a charge, and that energy could be potential or it could be kinetic, depending on our situation. You could also simply rewrite this as KQQ over R, which leads me to this little diagram that I drew up. I learned about this in my freshman physics class, and it's kind of stuck with me ever since, just trying to keep the same thing straight. So here we have our 4 main electrostatics things. We've got force, we've got field strength, we've got potential difference, and we have energy. And they form this really neat little, I guess, neat to me, box around here. So if I take the force and divide it by the charge, I get field strength. If I take the field strength and multiply it by the charge, I get the force. Field strength multiplied by R gives me potential difference. Potential difference multiplied by Q gives me the field strength, or gives me the energy. Energy divided by R gives me the force. And back and forth and around we go. For me, this was a little bit simpler than remembering all the 4 different equations. I'm going to remember one of them, and I'm going to remember the rough path around there. Again, may not be your thing, but when I saw this as a freshman in college, this was, oh, this clicked for me. So here it is. I hope it clicks for some of you as well. All right, and then we've got a next poll question. So let me open this up. Another multiple choice question, and ready, set, go. All right, this one's interesting. A little bit tougher than the previous ones. About 10 seconds left, then we'll go over it. And again, don't feel bad about making a mistake here. If you're not sure, guess like you would on the exam, and then we'll talk through it. 2, 1. All right, let's publish those results. Okay, so we had some people jump around and change some answers a little bit, but the correct answer here is C, 2,400 volts. Now let's talk about why. So I'm going to grab my equation off here, and I dropped the integration sign because we're just dealing with a single point. But potential difference is the electric field strength dotted with the radius. And I chose this one because, well, we're given E in the question. We're given electric field strength, and we got distances, which to me says radius and stuff like that. Because it is a dot product, we only care about the parallel components of that. So for those of you who chose D, I see where you're going. You did a 3, 4. Hey, this must be a 5 right triangle. So 0.3, 0.4, 0.5. 0.5 times 6,000 is 3,000. True. But the electric field is only parallel with the 0.4. Okay, so we're only using the parallel component of the radius, which is why we did 0.4 times 6,000 to get choice C. Okay. Some other options on there that maybe we're thinking about here. 0 volts. This one is a little bit easier to get rid of because we do have an electric field and we are moving from different points in there. Now I see where 0 could happen if X was down here at the bottom and we moved all the way up perpendicular to the field, there would be no voltage. And then that would be the right answer. But so this would be the perpendicular part. We don't care about that. B, you guys did 0.3. Again, doable, but we care about parallel for dot product, not perpendicular. So choice C was the right answer. So I hope this one clears up some misunderstanding in there. But all these answers are mathematically doable, which is why this question was a little bit tougher. There wasn't one I could easily throw out and say, this is obviously wrong in there. Okay, so that was some multiple choice. Again, we're going to expect most of the, or maybe a quarter to a third of the multiple choice questions to be about electrostatics. I would also expect a free response question on electrostatics. Okay, so we're going to go over this one. This is 2001 Q1 as an FRQ. Again, if you're taking the exam in June, the same sort of stuff could be asked to be done just as a multiple choice question. So still do these. I'm going to give you guys 2 minutes to get your thoughts down for this. Sheet of paper, scrap paper, anything like that, or even just mentally think through it. Then we'll go over it. We're going to go part by part. So just part A, then just part B, et cetera, et cetera. And 2 minutes is roughly the amount of time that I would recommend spending on this. This would give you a couple minutes to do it. And then if you finish early on another part, you can come back and fix it or whatever on there. So I'm going to start the clock, get your thoughts down, and then we'll go over this part A in roughly 2 minutes. All right, and that is 2 minutes. So roughly, that's about the amount of time it should take if you're going to stay on pace for these. So let's take a look at the scoring guides for this. So part 1, or part A, I put it that way. Click. Come on. There we go. Is worth a whopping 4 points. This is quite a lot. I mean, this question as a whole is worth 15. And we'll often see a lot of times they're going to front end the points on this sort of thing. So let's break it down a little bit. You get 1 point for simply finding the right equation for determining the electric field. Hey, this one's right off your reference table. There's nothing crazy or difficult about getting this first point. We got to find the right equation. And how do I know the right equation? Well, if I look back, I'm seeing things like, hey, I'm given charges. I'm given distances. I'm given electric fields. So if I'm looking for Q's, R's, and E's, well, there's only one equation, I think, that has all that stuff in it, and that happens to be this one, KQ over R squared, summing them up. And why are we summing them up? Because we have 4 different charges going on. So 4 different charges. We've got the 2 negative 30, positive 30, negative 30, positive 30. So 2 in the cloud, 2 in the ground that we have to worry about for all of these things. So we want to sum them all up. And they give you a point for summing them all up. And they do say in here, for their case, they're calling up positive and down negative. But as long as you make the choice that you're going to call one direction positive, the other direction negative, and stick with it, we're good. They give you a point for putting in the right values. So simply putting the right numbers in the equation gives you a second point. A point for the correct answer, whether it's fully done all the math, or they're even letting you do it in terms of 4 pi epsilon naught or K. There was a question earlier. Does it matter? No, it doesn't. Either one's good there. And the last point comes from the correct direction. Okay. And then again, a little bit here because you had to do 4 points. If you had 4 different charges, if you only did for 2 of them, they're giving you 3 points maximum if you did that work. So you're going to lose 1 point for not including all the charges in there. But overall, put down the equation. You got a point. Plug in the numbers. You get a point. Get the right answer. Do the math right. You get a point. And put the direction on there. You get a point. Okay, because again, it does say direction and magnitude for this question. We need to make sure we're including both of them in there. All right, so that's part A. Part B, again, 2 minutes, and we'll work through this one. All right, about 30 more seconds to go. All right. And that's 2 minutes, right about now. Or close enough. We'll call it close enough. All right, let's talk through this one. All right, so first part, we're asked to draw and indicate the direction of the electric field at point P2. Okay? And then compare it with magnitude at point P1, justify your answer. All right, now I know someone somewhere is saying, well, wait a minute, Peter. If I didn't get the right answer for part A, how am I going to get the right answer for part B? And there's a really simple way of doing this. And it's the exact same thing I tell all my kids. If you don't get an answer for part A, write down an answer. Make up a number. And then use that number in your explanation for part B. So let's go through this one. So 1 point, clearly indicating the direction. So in this case, it should be going up. Why should it be going up? Well, it's the same exact thing as point P1. It doesn't really matter. We still have more charge above than below, or sorry, we still have positive charge above, negative charge below. It should be pointing upwards towards that negative charge. That part should not have changed. Right? But what has changed is we should have less electric field strength at point P2 than point P1, simply because the distance from here to here is greater than the distance from here to here. Okay? So because we are further away, that hypotenuse is a little bit longer than the leg of one of these triangles, there must be less force. So they give you 1 point for checking less. They give you 1 point for explaining it. And it could simply be, hey, P2 is farther away than P1, so the field should be less. Great. Now, here's the other part. If you decided to work out all the math, which is about 45,000, you would get it for basically any number that is less than 75,000. So if you did the math out and you got that your answer was less than your work in part A, cool, that's good enough. Also, you could go the other way around. If you, let's say you screwed up part A and got an answer of like 10, I don't know, I'm making up a number here. And then you did the work for part B and said, hey, 45,000 is bigger than 10. And you checked the greater box, I'm willing to bet they would give you points for that because your justification and checking is going to match up your previous response. The no points part here is simply saying, hey, if you did part A right or left part A blank or something like that, and then checked the wrong box and tried to explain it, that's where you lose those points. So if your response for part B does not match and line up with your response for part A, they won't give you those points for the justification and stuff like that. But again, here's another great case where simply checking a box gets you 1 point. And maybe that's, you have no idea how to do the question. You got a 1 in 3 chance of getting that one right. And that's a nice freebie point there-ish. Same deal with the first one. I would draw it the same direction your arrow was going for part A and make it that way. There should be very, very similar sort of things going on there. Okay, next part. Now we're looking for potential difference in here. And they are saying, assume the 0 to be infinite, which means we should be dealing with pretty much all, well, if 0 is infinite, we should be beginning with positive numbers going down. So 0, and then the closer we get, should be more and more and more positive. So let's take 2 minutes for this. Here we're going to look at the voltage or the potential difference for those things, 0.1 and 0.2. right, another 20 seconds or so for this one. And then we'll keep going. Again, just a reminder, if you guys have questions that you'd like answered, right below the stream here, feel free to put them in that Q&A chat, and we will answer them as quickly as possible. All right, so let's go through part C. Part C, basically we want to find the potential at point P1 and point P2. Well, looking at this, I know that the potential is going to depend on the charges above and below. So let's start there. And I'm going to go to my reference tables, and I'm going to find the equation potential equals KQ over R. And I'm going to add them up. And if I add them up, notice that, well, we're seeing a lot of things that happen to be the same exact number, except for positive or negative. I've got a negative charge and a positive charge exactly the same distance away. And I got a positive charge and a negative charge exactly the same distance away. So you could argue simply from symmetry that the potential has to be 0, or you could do the math out and have it be 0. But realistically, this is kind of a crazy question where you can simply say V equals 0, show no work, and get 2 points for it. Now, would I recommend doing that? No. I would much rather have you do the alternate solution here. Use the equation, plug in the numbers, and that way, even if, God forbid, some crazy math mistake happened, you still get half the points because you are showing a correct formula for determining the potential. Okay. And then the same thing for the second one, where you were able to basically do the same sort of thing or do the same equations out here. Here they're doing a right triangle because they told you how far P2 is away. P2 is 1 kilometer horizontally. So you can do a 1, 2, square root of 5 right triangle. Sorry, 1, 2 square root of 5 right triangle for the lower charges, and a 1, 3 square root of 10 right triangle for the upper charges, and write those out. And again, you see the same exact thing. We're getting positive, negative. Sorry, positive, negative, positive, negative. Those potentials cancel each other out exactly, and we are left with no potential at P1 nor P2. They are both the same exact thing. And again, this is one of these weird ones where you can get perfect credit for saying 0 and 0 with no work being shown, but I really don't recommend that. Please at least show an equation so that if something goes wrong, you at least get half the points. And remember, half the points is almost, well, most of our way to our 5. So there we go. All right, next part. I put D and E together for this one just for time's sake. I'm going to give you guys 2 minutes. Let me know in the questions, or let Danny know if you want more time for these multiple part ones, but we'll see how it goes. right. Coming down to the wire. 15 seconds to go-ish. We're doing pretty good. All right, so let's take a look at this one. Now, I am shortening these just so we make sure we have time to cover everything in the stream. Normally, if this was the actual question, we would have about another 6-7 minutes or so to go through these. But again, I'm shortening it so we have time to get this done here. Both of these are pretty much the same exact sort of stuff. So for D, again, we're looking for potential. So I'm going to do KQ over R. And now we are looking at 1 meter or 1 kilometer, 1 kilometer above point P1. Okay, so now I'm looking somewhere up here by this Q in FRQ. So now I would do, okay, so the plus 30 is 1 kilometer away. The minus 30 is 2 kilometers away. And down here, this would be 2, 4, 5, 6 kilometers away. And then the minus 30 at 7 kilometers away. So that's how we're getting the numbers here for these different parts in there. And this one, because we are asked to determine, means we're looking for a number. Plug it in and go. 1 point for the equation, 1 point for plugging it in. That's about it. Also, notice here that they're not penalizing you for changing kilometers to meters. We should, because meters are our base unit in physics, but you're not losing credit for this. I can't guarantee that will always be the case. So please make sure we're putting them in meters with that 10 to the third on all the numbers here. Okay. And then part E, we're looking for potential energy. Okay. I would like to use U equals Q times V, but you can do the other part too. That works perfectly fine here. And we're plugging stuff in. 9 times 10 to the 9th is the, wow. Yeah, that's K in there. So K, right off your reference tables. Q, V, boom, 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 boom. Add them all up and go from there. Okay. And we have 6 possible combinations because we have all the different possibilities between the charge pairs going on here. And then we're left with roughly negative 1.6 times 10 to the 10th joules of potential energy. All right. So we're looking at summing Q times V. And we would go with 1, 2, 3, 4, 5, and 6 different possibilities there. All right. And that is electrostatics. That is the pure plain stuff. Okay, let's switch over to Mentimeter for a second here. Again, let me go to the next question. Whoops, I suppose we should have answered this one already. I'm going to skip that one for now. So I'm looking at, again, menti.com 348474792. And give me a kind of range here. Where are we feeling on these topics? Is it still something we need to go over more? How confident are we feeling on these things? Go on there. And once you answered that, let's take like a 3-minute break. Relax, get a cup of coffee, go find some dinner, whatever time it is for you. We'll meet back up here in a few minutes to go from there. Okay, cool. So charges are looking pretty good. Potential difference is still a little iffy. I completely understand that. We were bouncing around here. Electric potential energy is getting down a little bit. Okay, so we're scooching up. Good. Well, I am looking at this so far. This is pretty good. Charges and Coulomb's law and electric fields are probably the big topics on there. Potential difference is going to show up mostly in that V equals equations. And electric potential energy, honestly, that's the one that is going to show up the least on here. If it does, it'll be kind of like in that previous FRQ where it's just, here, tell me what it is, and you plug numbers into an equation on there. So, all right, cool. Good. I'm glad that we're high up in the Coulomb's law because, like I said, those are the ones that are going to get used the most. And then we're kind of in the middle for the other ones. That's you're okay if you're in that range. So cool. Good. All right, let's take a couple minutes. I'm going to go through and answer some Q&As that are posted below. And we'll pick this up in like, let's say 2 or 3 minutes for that. So let's see what we got. Okay, so we've taken a little break here. Let's move on to our next topic, which, as somebody just asked in the Q&A here, is Gauss's law. Gauss's law kind of deserves its own separate topic, because out of electrostatics, it's kind of broken down between the two parts. There is Gauss's law, which is kind of the key fundamental part, especially on free response questions. And then you're going to see like Coulomb's law and electric field strength and stuff like that done kind of separately. Although there are some questions where they come together. But let's knock out Gauss's law right now. So Gauss's law is great for determining how much charge we actually have in a given surface or area. So Gauss's law simply states that the sum of the charges, or the charge sources, positive charges or negative charges, within a closed surface, so got to be a closed path, a closed cylinder, sphere, is equal to the total electric flux through the surface. Now, somebody may be reading this for the first time and saying, okay, what's electric flux? Electric flux simply is the field lines entering or passing through, either entering or leaving a given surface. Simply put, if the number of field lines entering a given surface is the same as the number of field lines that are leaving the surface, there is no charge inside that area. If there are more field lines leaving than entering, we've got a positive charge. If there's more field lines entering than leaving, we've got a negative charge. And that's kind of how Gauss's law works through there. And most of the time, it's going to be written in this form: the integral over a closed surface of E dot dA. Again, dot product parallel matters. Will equal the Q, or the closed charge, over epsilon dot. In there. So how do we do Gauss's law problems? Because a lot of the times we're going to be getting into not so much what is Gauss's law, but how do we apply it? How do we figure out what surface we're going to use to put around this object? How do we figure out how much charge is in there or not in there, or what the strength of the field is or not? So my tips, how I would do this. Number one, I'm going to look at what kind of surface do we need. If it's a single point where I can enclose this thing in a three-dimensional sphere, great. I can do that where the area is pi r squared, or a circle and the area is pi r squared, because again, I only care about the parallel parts to that. For a plane or a sheet, a line of charge, I can use a cylinder to wrap it around it, and the area for that is 2 pi r. And for a line, I can also do a cylinder, which is 2 pi r L. Ideally, I'm going to try to use symmetry, kind of like how we did in the previous FRQ with voltage, to see if I can simplify this down a lot. If I can, great. And then I may need to redesign the surface and stuff like that. And then we'll just kind of plug and chug, do some solving of this. And just a side note, this is not super common, but sometimes we include a dielectric in our material. It will just change a little bit where we have to include the kappa, the dielectric constant, in with our Gauss's law. Most of the time, we're talking about this being air or free space or a vacuum, where kappa is 1 and we can ignore it. But every once in a while, you might get a question that says, hey, we have this special oil or this special dielectric in there. How is that going to change it? We just add kappa in there. Okay, so there was a request to do a little bit longer on these free response, or these multiple choice questions. So I'm going to open up the poll now, and I'm going to wait for a good 15 seconds before I click play. So here we go. Poll should be open. We've got a Gaussian cube with sides of S enclosing a single point charge plus Q. What is the flux through one face of the cube? And play. All right, 1 minute to go. Vote in the poll. Let's see how we do. Okay. Oh, hold on. Oh, no. All right, so time is just about up. I'm going to preface this before I say show, saying that I checked the wrong box on this poll, and the right answer that it's going to say is not the right answer. The next slide will have the correct one. So I'm just going to leave this poll as, hidden and invisible because it's not the right answer that's shown here. So we'll just pretend like I chose the right one because that's what I did. The correct answer here is C. And there were really breaking it down. Some of you are choosing D, which, sure, that's the area of a side going through there. That kind of makes sense here. But C is the best answer. And the reason for that is, if I go back to Gauss's law, I know that the entire flux over the entire area of the sphere, or the cube, must be equal to Q over epsilon naught. Okay? Which means that since this cube has 6 sides, and there's nothing special about a side, they're all identical to each other because it's a cube, each side must have 1/6 of the total flux. Which means, here's my total flux right here, Q over epsilon naught, and 1/6 of that gives me choice C on there. So good job for those of you who chose C. I did see some Bs. That would be the total flux. And then, like I said, D divided by 1 over side squared is not going to give you that part, or the correct answer there. On there. And notice the Vimeo doesn't let me do E polls, so E couldn't have been the right answer either. A doesn't make any sense because we're enclosing a charge. So because of symmetry, because we have to have 1/6 of the flux going out each side of this cube, the flux coming out one side of the cube must be 1/6 of the total flux. All right, let's take a look at another one. Can I publish and archive? There we go. Hopefully I chose the right answer for this one now. We'll see if that works. Let's open this poll up. We're doing the same sort of thing. We have a very long rod showing the positive charge uniformly distributed among its length. The electric field at point R naught from it is E naught. What happens if I move that 5 times the distance? What happens to my electric field? All right, and this one's in the books. Okay, so this one, at least if you didn't get, if you weren't solid on the answer, we can at least eliminate some choices pretty easily here. Okay? So if I'm going through this, first off, I know, and nobody here chose these answers, which makes me really happy. The farther away I get, the smaller the field should be. Okay, because the farther I get, the smaller the force is, and the field depends on the force, so it should be smaller than it started off as. So because my distance is increasing, my force will decrease and the field should decrease. So it can't be D and it can't be E. And nobody chose those options. Those were not ones that were shown up on here. So that's really good. Now we're stuck between A and B. And I guess a couple of people chose C. Not a bad guess, saying that, hey, it doesn't matter. But it actually does matter on there. So let's go through this. So we're going to enclose this in a cylinder and assume we're using some sort of linear charge density. This is lambda, and it is equal to the charge over a given length of this rod. Because really, we only care about a part of this rod, the length, the set L part in here. And we're going to go through and let's apply Gauss's law to that. Over our closed cylinder, we are going to enclose a certain amount of charge divided by epsilon naught. The area of a cylinder, or the surface area of a cylinder, is 2 pi r times L. So this is one of the ones that we really should memorize. The area of a cylinder, surface area of a cylinder, is 2 pi r L. And that is equal to, well, if I rearrange this for Q, I get lambda times L over epsilon naught. The lambdas disappear, the L's disappear, and I'm left with E over 2, or E equals lambda over 2 pi epsilon naught R. Notice how R is in the denominator, and it is to the first power. It is not squared, just to the first power. That means my field is proportional to 1 over R. Because my field is proportional to 1 over R, if I make it 5 times further, it should give me 1/5 of the field. All right. For those of you who chose A, you had it maybe being like 4 pi r squared for a sphere, but I really can't wrap a sphere around this. This is a very long rod. It doesn't make sense to do a sphere. And I guess the picture is slightly misleading here. But if we extend this on, you do get a cylinder around that. And that goes with the tips I showed in the previous one here. For a line of charge, we're going to use a cylinder to do that. So, and that might be one where it's just worth memorizing those sort of things. When do we apply a cylinder? When do we apply a sphere? When do we apply a shell on there? And by the way, the slides are linked right below this too on the other resources tab. So feel free to print that slide off and just carry it with you until tomorrow and then throw it away before the test. But because it's proportional to 1 over R, we get 1/5 of the electric field. Okay, so that was some sample MRQ, MCQ questions for Gauss's law. Now we're going to get to one that you'll probably see on the exam. Again, historically, your 3 free response questions are going to be 1 on electrostatics, which normally is a Gauss's law one. You're going to get 1 on circuits and 1 on magnetism in some form. So here's a sample one. This is from 2012. So getting a bit older, but very similar to ones that you might see tomorrow on your exam. All right. So same deal. I'm going to hit play, give you guys about 2 minutes to tackle this one to the best of your ability. Then we'll go over it and go from there. All right. And just about 2 minutes for that question. So let's go over it. All right. We have 2 conducting shells. And the shells part here is our clue of what type of surface we're going to use for Gauss's law. We're given radii. We're given potentials. We're given other potentials. we're looking at charges on the two spheres, and r is the distance between them. Let's find Gauss's law for 0.1 to r to 0.2. So we are between the two shells. So if I were to draw my Gauss's law surface around here, I would fully enclose the inner shell, but not touch at all the exterior shell. All right, so point-wise, we get 1 point for simply writing down Gauss's law. Copying it off your reference tables gets you a point. All right, we also get a second point for writing down that the surface area of a sphere is 4 pi r squared. Again, this one also comes off your reference tables. Let's see if I can bring this into play here. And there we go. I think that's showing that the surface area of a sphere is 4 pi r squared. So right off your equation tables, don't need to memorize it, just need to know, hey, this is on the last page of my reference tables on there. Okay. And then you get your third point for simply plugging stuff in. Well, Qi is what they told us to use for the charge. And yeah, we're able to get simply 1 over 4 pi epsilon naught Qi over r squared, kind of subbing and stuff like that, dividing by that over. Or, again, this is one where leaving it as epsilon naught may make a little bit more sense. Or you could remember that 1 over 4 pi epsilon naught is k, and leave it as kqi over r squared. Either one is fine for this case. Okay. Yeah, this also, by the way, is very, very, very similar to a point charge that we saw back in the previous chunk of slides. So, yeah, just noticing that interesting fact. All right, so part A was going in between the two shells. Let's do part B when you have the entirety, the whole thing encapsulated. Let's find the electric field for that. All right, another 30 seconds through here. And as you're working here, I just want to point out the difference in the task between this one and part A. And we'll go over that in more detail in a second here. But the difference between derive and determine in these two tasks. All right, so I mentioned just briefly here, we have determine for part B, but part A said derive. That's going to make a slight difference in how we are doing the points for this and where you're getting your credit for. For derive, you got a point for simply writing down Gauss's law because it was derive. Start with the fundamental equation. For determine, now this time for part B, determine, I don't get a point for writing down Gauss's law. I simply get a point for saying, hey, Gauss's law must have the total sum of all the charges inside it. So Qi plus Qo over epsilon naught, and then write it down. So we still have that same sort of spherical surface area as before, and go from there. You could also have just written down the final answer here. Taken what you did in part A, realize that, hey, this depends on Q being the total charge we're going to enclose. I'm still using the same shape. I still get R as my variable. Let me just sum the charges in here and I'm good. And that will give you both points as well. Now, would I recommend doing that? No, I'd recommend doing the two-step method they're showing here. But if you're confident enough to go with it, then go with it and save yourself a little time. Part B is one of those parts where this is one where I feel like we should come in under the 2-minute time clock and save that time for a different problem or a different part. All right, part C. So now we've done Gauss's law stuff. We've got E being done. Now we're looking for the electric potential, looking V of R for when we are outside of both of the two spheres. 2 minutes, ready, set, go. All right, another 10 seconds on this part, and we will go from there. Okay, so let's take a look at this. We're looking for V now, so electric potential, which means I'm kind of looking more for equations that solve for V. Maybe doing something in this range where I'm doing negative dV dx. The integral one might be useful. Summing all the Qi and Ri parts could be useful as well. So I'm kind of gravitating to somewhere in this range on the reference table. And actually, there's two possible ways of doing this. One for each of the equations. Who would have thought? So you could get 2 points by going through and finding the integral definition. The change in potential is equal to the negative integral of E dot dr. Well, potential at infinity is 0. The question told us to assume that. So 0, great, that's easy. Negative going from R to infinity. Notice the flipped bounds here. On there, K Q's over R squared dr. This is the same part we just found in part B. So plug in the E we found when you're enclosing the whole thing, because that's what we're doing in this case. And we get our bounds. We're evaluating negative 1 over R. Everything else here is a constant, so just pull it out. The integral of 1 over R squared becomes 1 over R with the negative sign. And then we just evaluate it from those bounds, and we get 1 over 4 pi epsilon naught Qi plus Q naught over R. 2 points. 1 point for using the integral definition. I don't think it actually says anything about plugging in. It just simply using this gets you 1 point. Okay, and then 1 for the correct answer. You could also have chosen to do the other equation, where it's the summation of all of the potentials. And we would say, okay, so I've got potential from the inner shell and a potential for the outer shell. Adding them together because we're enclosing both those, and we end up with V of R, the exact same equation here, a point for using the concept of adding them. So again, writing down the equation gets you 1 point, and then plugging stuff in gets you the other point. Not bad, and really pretty simple to get at least 1 point just for writing down the equations for this part, even if we don't go any further than that. All right, and the final, hold on. No, there are more. I don't know why I said final. The next part of this problem, sorry, using numerical information given. So I have some V's going on here, some R's that have been given. Calculate the value of the total charge, QT, on the two spherical shells, where, hey, QT is the sum of the two charges. All right, 2 minutes. Let's go knock this one out. All right, and time is up right here. So let's take a look at this part. We're trying to find QT. So this one, 1 point. Not a ton of work to do here, assuming you got part C. And that's one of the tough parts. If you didn't get part C, this one becomes a little bit tougher to do. But basically, we're taking the equation from part C, and we are simply just plugging in the values. R is bigger or equal to 0.2 meters, so we'll plug in 0.2 meters. The question tells us that the voltage on the outer shell is positive 100 volts. We know what 4 pi epsilon naught is, so we've got that going on right there. And we end up with the total charge being 2.2 times 10 to the negative 9th coulombs. So kind of a plug and chug, which is why it's only 1 point. And yeah, it simply just says correct work, resulting in the correct value. Notice how they did say with units here, meaning if you did not put units on your answer, and probably units on your work, the way it's worded, you would not get credit for this part. So always, 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 when you're showing work and you're doing numbers, put units on, please. All right, next part. Here we're doing graphs. Again, I've said this before, but whenever you get a graphing question, do not leave it blank. Even if you just sketch some random stuff on there, there's a chance you can get points for it. And graphs typically are worth a lot more points than you might think. So answer the graphs, do it all. And let's take a look at this next part. 2 minutes, ready, set, go. All right, another 30 seconds or so to get through this one, and then we'll go over it and go from there. All right, cool. So for this one, we're trying to find the E field as a function of radius. Remember, most of the time we're talking about electric field being 1 over R. So that should be our kind of clue of what we're looking at here. The only times it's not is when you're inside of a insulator, and then it would be linear. But in this case, we're not. We're talking about conducting spherical shells. There's nothing inside here to worry about. So this would simply just be, hey, we are inside a conductor. Great, we are inside this conductor. The E field inside a conductor is 0. So there's nothing going on inside this conducting shell because all of the charge would be on the surface of it. So flat, nothing going on everywhere from 0.1 downwards. So we are no charge enclosed, so no E field going on there. So 1 point for this chunk. Then at 0.1, we can immediately jump down to some value. Okay. Now, notice in this case, they say sketch. All right. Sketch does not mean I need numbers. They're putting these on here just as reference. They are not to scale, and you do not need them to get credit for this question. That's why it's sketch. If it was plot, we'd have to worry about numbers. But because it's sketch, we don't care about it. 0.1, we should have some negative E field value. Why negative? Because we have a negative inner ring. We are told that the potential difference on this ring is negative 100 volts, which means we are having a negative E field in there. We then can curve it, 1 over R. So we start large and we are decreasing as we get more and more and more radius. So we should have a curve here, concave down and negative values. At 0.2, we suddenly have now enclosed both spheres. Enclosing both spheres means our voltage is now positive 100 volts, which means it's a positive E field. And again, we're going to jump up to some positive value. I'm not concerned about the number. I'm concerned that it's positive. And then again, concave up because it's 1 over R decreasing. And you can have this asymptote out, but it does say we better not touch or cross the horizontal axis because we will never have a 0 field until we get infinity, and we don't have an infinite axis here. And we better not go negative because that would mean that we're enclosing more charge somewhere that doesn't exist. Okay. For the sake of time, I'm going to jump ahead a little bit here. We'll finish up this FRQ. There's one more part to it. Then we'll jump to capacitance and then take a break after that. So let me play this one. We're doing the same thing, except for now we're doing electric potential. And 2 minutes on this one. Ready, set, go. All right, and there is time for this one as well. So now we're graphing potential as a function of R. Right? Again, it's sketch, which means the numbers on the graph don't matter. This one, again, pretty straightforward. The first sphere, we have a negative voltage. They told us in the question, so let's hold that at negative 100 and constant. Once we get out of the first sphere, we are now going to be rising up until we hit the 100-volt potential. Once again, V depends on 1 over R, so we're getting this curve and this curve sort of thing going on here. And really, they're looking for a constant negative potential. Gives you 1 point. They're looking for discontinuities. The voltage changing very obviously at 0.1 and 0.2. So constant negative there. Increasing concave down crosses the r-axis for this chunk. This is where we're going from negative 100 all the way up to positive 100. And changing as we go through there. It's not linear because we are looking at the total enclosed charge changing as we get up there. So it's not, we're not enclosing charge at a linear rate, so our voltage will not be a constant either. And then we hit 0.2. Now we enclose the entire charge. There's no more we can enclose, so now we're just simply getting farther away. And as we know, the farther away we go, the more the voltage will trend to be 0. So this will start going down. If we continue this on, this will asymptote forever, reaching 0 at an infinite distance away. But 4 points for this part. What was the other part? 3 points for this one. That's half the points on this question for 2 graphs. Really, really important that we are not leaving graphs blank on this exam. Really, really important. All right, I'm going to skip this one for a second. We'll come back to the brain break in a bit here. I just want to touch on capacitors before we take our break here. Capacitors are one of these concepts that is rarely done by itself. Most of the time, we're going to see this in the context of a electrical circuit question or as a electric field parallel plate sort of thing like that question. But it does show up every once in a while. Capacitance is the idea that a capacitor is storing charge on the plates, and it will store charge on the plates until the voltage on the plate is equal to the supply voltage, the battery or whatever power source we're applying to it. How much it can store is called the capacitance, and that depends on a couple factors. The area of the plate, the distance between the plates, and again, this epsilon factor here, which may change if we add a dielectric to it, which I think is my next slide. Nope. Skip ahead here. So dielectrics will start adding in this kappa term and then changing the capacitance of it. It's a material that's designed to increase the capacitance in there. So simply useful. It's typically material that's easier to polarize. So it's going to store more charge in there. Okay. Now, capacitors, most of the time you see parallel plates, but you can also have spherical or cylindrical capacitors. Again, I'm not expecting you to be asked to derive this part, but here's the gist of it. If we take a look at a spherical capacitor, the electric field for that capacitor is Q over 1 over 4 pi epsilon naught R squared. Plugging that into the voltage equation, the change in voltage is the negative integral of E dot dr. We run through, we keep doing the math out, and we get the change in voltage is 1 over 4 pi epsilon naught R1, or 1 over R1 minus 1 over R2. Well, we plug that into the capacitance equation here, plug some Q's in, and we get capacitance for a spherical capacitor is 4 pi epsilon naught over the inverses of the radii subtracted from each other. For the cylindrical one, we do the same sort of thing. We define lambda as our charge density, again, our linear charge density, and go through the same sort of thing. Change in voltage, integrate it through, and we get, again, this lambda equals Q over L to get rid of the lambda part. We end up with this one a bit more complicated because of the cylindrical nature of it. 2 pi epsilon naught L over the natural log of R2 over R1. Again, I am not expecting you to be asked to derive those, but it is possible that you're going to get a situation where the capacitor is not a linear parallel plate capacitor. If you do, simply, I'm going to assume they're going to give this to you and say do something with it. But there's always the chance of taking, okay, let's find the E field for that particular structure. Let's plug it into the voltage equation, do the calculus, and then plug it into the capacitance equation to find C. Is typically how you're going to do it. Okay. Yeah, where are we here? The capacitors also store some energy, and that makes sense. That's the whole point of us using capacitors as an energy storage device. We'll hammer this more when we get into circuits, which will be after our break. But the gist is each little bit of tiny charge stores a tiny bit of energy. And we're just going to use the definition of electric potential energy to be VQ. So differential form. We'll turn it into the integral form. We'll plug in Q over C for voltage. We'll integrate it from our bounds, and we will end up with the energy stored in a capacitor is 1/2 Q squared over C squared. And then using the capacitance definition, Q equals C over V, we can also get 1/2 QV or 1/2 CV squared. Depending on our use case, one of those will be better than the other. This is given to you right down here. UC is 1/2 QV or 1/2 CV squared. And again, if you need to, you can do V equals Q over C to solve the rest of the parts. There are capacitance in series and parallel equations as well. We'll hit those when we do circuits. So we'll come back to those in a smidge. All right, you know what? Before we hit this capacitance question, let's take a 5-minute break. Enjoy some nature, picture yourself outside, relaxing, stuff like that. I'm going to go get more coffee, and I'll be back in like 5 minutes. All right. Just a reminder, as I'm going through, you can also, don't forget, put questions that you want answered down below in the chat. Not in the chat, in the Q&A part. And Danny is doing a great job answering those quickly. So again, if we're going through those when you got a question, answer down below. All right. Let's tackle the capacitor one together. Just because we are running a bit slower than I had planned, and I want to make sure we have time to get to the other stuff in there. So if I'm going through the FRQs, again, I'm not going to do the time part. We'll just talk through these here. So we have a capacitor. This, by the way, is 2000. Older question, but this is one going through the capacitor is kind of like a standalone. This would be your typical electrostatics question, just with a capacitor instead of a point charge or something like that. So we got a capacitor, two conducting coaxial cylindrical shells, A and B, blah, 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 blah. We're filling with oil that has a dielectric constant kappa. This is where we have to make sure we're including kappa in our Gauss's law equation because of that. Initially, both cylinders are uncharged. We charge them like a capacitor, plus Q on the inner, minus Q on the outer. R is the radial distance from the axis. Okay, so Gauss's law, determine the electric field midway along the length of the cylinder. Good, so we get to ignore any sort of ends here. We can just assume we're in the center for the following values of R in terms of the given quantities and fundamental constants. So for I, we are between A and B. So we are somewhere between there, and then B, we are, or double I, we are outside the area. Okay, so for the first part, 3, we are going through and stating Gauss's law. Well, that makes kind of sense. We're doing Gauss's law stuff. And notice we're talking determine, derive, that sort of stuff like that. In this case, we're getting a point for the law. Sometimes we're not, but in this case, we're getting a point for it. And we also get a point for talking about the permittivity of the oil in terms of kappa. This is where we mentioned before that if you have a dielectric, it's not over epsilon naught anymore. It's over kappa epsilon naught. And then we get the correct expression for the field in the oil. So again, because we have a cylindrical shell, we're going to use a cylinder for Gauss's law. That makes sense. And if we're looking at a cylinder, surface area of a cylinder is 2 pi RL. We're ignoring the end, which is why I'm not worried about this 2 pi r squared part. And we simply plug it in and solve for E. Okay. For double I, this one's actually even easier. We're looking at enclosing the entire cylinder, or the entire radius, the side profile of the cylinder. We have plus Q on the inside, minus Q on the outside. Well, guess what? Those added up give you 0. So there is no enclosed charge, and that means our electric field is 0. So really, we could probably get away with saying because the enclosed charge is 0, the electric field is 0, and that'd be fine for that part. All right, part B, doing the same thing, except for now we're looking for potential difference and capacitance for this sort of thing. So running through again, here we go. For the first part, we're going to use, again, the integral form of potential difference, or electric potential. Same difference now. That's good. Same thing. In here, where we're going to look at between B and A, because this question is looking at across the capacitor. So we want to include the A radius as one side of the capacitor and the B radius as the other side of the capacitor. That's where those bounds come from. We get a point for simply writing out that. Nothing too fancy there. We get a point for substituting in the potential difference, or sorry, the electric field equation, which we got in the previous part. And then we get a point for integrating it and ending up with our natural log of B over A. Pretty straightforward. Point for the equation, point for plugging in, point for the answer. And then double I, this one, again, very similar. You're taking the capacitance equation and rearranging it for C, plugging in the right Q, and that's it. So really straightforward for this part. Assuming we had the right E, and even if we didn't, if we wrote down an E that we could use again, we'd be in fine shape using whatever answer we got for part A in I and double I to get the answers. All right, and here, brain break. Let's open up Mentimeter again here, and let's do the next chunk on capacitors and Gauss's law. We spent a good while on it, but let's see how we're feeling. How are we feeling with Mentimeter on Gauss's law, capacitors, doing charge, voltage, and energy? And even the energy one, again, we'll hit that one later on again in circuit. So if that's a little wonky, we're coming back to that one as well. But hopefully we're better on Gauss's law than we were feeling at the beginning. So go ahead, hop on Mentimeter, and do show the stuffs. Okay, not too shabby. All right, not bad as we keep getting answers in. And this is realistically really, really encouraging because Gauss's law, most of you guys are going up to the upper end of Gauss's law there. Gauss's law, I can almost guarantee, I would almost bet money on Gauss's law being a free response question in there. Charge on a capacitor is probably going to show up there as well. Voltage will be, again, we're going to hit this one again when we do the circuit part, so understandable. And energy, again, we're kind of in that nebulous range. Energy for capacitors, actually energy for most of the stuff in this test is going to be here, just plug it into the equation and go. We haven't done a question on energy yet, but we will get to one in the circuit chunk as we move forward there. All right. So that being said, let's do a little diving in. Okay, so this is pretty good. Again, just a reminder, if you guys need to ask questions, there's a Q&A right below this chat or right below this stream. Please ask your questions there. Danny's doing an awesome job answering them, and I'll stop in too from time to time. So we're doing really good. Thanks for those of you who are asking questions in there, upvoting ones that you want to get answers to. Really, really, really solid in there. So good. All right. So let's move away from Mentimeter, back to the slides. Deep breath. We are done with electrostatics and capacitors. That is unit 1. That is unit 2. That is somewhere around 40% of what's on your multiple choice questions, and pretty much guaranteed 1/3 of what's on your free response questions. So good job. We are 2 hours in with 3 hours to go. So, whew. All right. Let's go on then. Next part. My favorite part, we're getting into circuits. Circuits is one of these concepts that I just love, and I feel like you can do so much with. Unfortunately, we're going to kind of skim through this part pretty quick because I want to get to the free response questions and the multiple choice questions because, again, I can pretty much guarantee one of your free response questions will be a circuit sort of question. So first, some terms. Current. Current is simply the rate of flow of charge. So dq dt, how much charge flows past a given point every second. If you want the more advanced, in-depth version of it, where we're talking about the drift velocity of charge carriers and the area of a wire and the charge of an electron or an elementary charge and the number of those passing by, okay, great. We got it right here. I equals NEAVD. This is one that realistically, I can't remember a ton of questions using this equation. And when it does, it's going to be blatantly obvious when you need to do it. It's the only one they're talking about drift velocity. So if we don't have a drift velocity mentioned, we're probably not touching this equation in there. But it's there. It's on your reference tables. They could ask a question on it. It might be a multiple choice thing. Maybe relating current to area. Maybe that's a possibility in there. But much more likely is we're going to be using I equals dq dt. And using Ohm's law variant, I equals V over R. So those are the super common ones to see on there. Resistance, simply defined, is the opposition of current flowing through a circuit. 2 ways we can define it. We got Ohm's law, graphically represented. Could be a great multiple choice question, talking about the slope of a current voltage graph as being resistance. And obviously, the more voltage for a given amount of current, the bigger the resistance will be. You could also talk about it in terms of wire resistance, where it's rho L over A, where rho is the resistivity, the natural conductiveness of the material. L is the length of the wire, and A is the cross-sectional area of the wire in typically meters squared in there. But this one, if you're going to do this, they're going to leave it in generic rho or give you maybe a table. But I'm betting generic rho would probably be the option there. Talk about a what if. What if we doubled the length? How does that change the resistance? What if we doubled the radius? How does that change the resistance? Just remember for A in this case, A is always going to be a circle. So pi r squared. I'm trying to think of a case where it's not. No, it's cross-sectional area. It'll always be pi r squared. So yeah, that sort of thing. We also have our power and energy equations. Power is given you on the reference table as this I delta V, which with Ohm's law, I squared R, V squared over R, those will all be useful depending on the what's given you in the question. But it's given to you as, where are we here? Power is I delta V, way down here at the bottom of the page. It's also, every once in a while, you may get a question about energy stored in a circuit or used in a circuit. Well, energy is just work, which is power times time. And that is just take the power one, throw a time in there, and you go. I doubt you're going to see one on here, but just in case, work is power times time. So keep it simple. and go from there. But you probably will see a power one in a multiple choice question and stuff like that in there. Maybe as a kind of throw in on the free response question and stuff like that. All right, circuits. I'm starting really basic because, well, I like circuits. So you got two types of circuits: series, one path, parallel, multiple paths. You've also, I'm sure, seen combination circuits where it's some of each. But the gist is, using circuit symbols, you've got some sort of voltage. Current comes out of the positive end, goes into the negative end through resistors. You've got your basic voltage, current, and resistance equations. And the features here, the key parts, which I like to keep in mind when we're doing multiple choice questions or what-if style questions. If something burns out or blows up in a series circuit, the whole thing stops. A circuit breaker in your house, a fuse in a car, a light bulb in a series of light bulbs on a Christmas tree, something like that. Series circuit, one burns out, they all burn out. Parallel circuit, we've got the same sort of thing. We now have 3 parallel branches in this case. Current goes through in the loops, 3 independent loops. Voltage for each branch is identical to each other. The current sum up as we go through. So the current splits here, goes down each path, sums back up to come back to the source. The resistance is the 1 over 1 over equation, or the 1 over Req equals 1 over R1 plus 1 over R2, dot, 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 dot. And if something stops in there, only that branch stops, and the rest of it works just fine. So I could turn off the lights in my kitchen without turning off my stove, hopefully. I can turn my cell phone, I can unplug my cell phone from the charger without turning off the electricity to my house. That sort of thing in there. Parallel circuit, super, super awesome and useful. And the combination between the two is how we wire everything. Common elements for a circuit, we've got resistors, we got capacitors, we got inductors. We'll come back to inductors after we've done electricity or EMI and stuff like that. So this will probably be our last unit for today, dealing with inductors. We'll come back to that one for a bit. But we've got resistors, capacitors, and all of our common equations. These are also, again, listed for you on your reference tables. So you've got resistors in series, resistors in parallel, capacitors in parallel, and capacitors in series. Again, series means one path between them. Parallel means multiple paths between them. All right. And with that being said, let's dive in to some circuit questions. All right, so I'm going to open up this poll again. Let's see, we are on circuits MCQ number 1. Poll is open. And here we have a simple circuit. Battery, 2 bulbs, and a switch connecting from there to there. All right, 2 identical light bulbs in series with a battery. When I turn them on, they both glow with equal brightness, and then I close the switch. What happens when I close the switch? Ready, set, go. All right, well, let's take a look. Okay, so we have a little variation in the answers here, but correct answer here is A, where bulb 1 gets brighter and bulb 2 goes out completely. Let's talk about the reason why for this. So the current flowing through the bulb tells us the brightness. That's kind of our generic touchstone for current is brightness. More current means brighter, less current means dimmer. So the majority of the current will flow down the path of least resistance. So in our case, to start off with, there was one loop, and everything would have to go out of or through bulb 1, through bulb 2, and back to the battery. That was the only path we had to work with. When we close the switch, however, we create a new option. We can now go through bulb 1 through the switch and back to the battery. That pretty much eliminates the possibility of any current going through bulb 2. Because 99.999% of it will go through the switch with bulb 1. And that means bulb 1 gets brighter because now we have made a circuit with less resistance, which means more current. And current is brightness, so bulb 1 gets brighter. Bulb 2 being broken by the short circuit basically will not get any current and will stay going out. For those of you who said C, slightly dimmer would mean that there would be still some current going through here. But basically, because we have shorted out bulb 2 completely with this switch, there won't be any current, or at least no significant current going through it. Not enough to make it light up. All right, next question. Capacitors in a circuit, because we love capacitors. Let's go through and take a look at this one as I open the question. This is question number 2. Open that poll. All right, 2 capacitors, initially uncharged, are connected in series, keyword series, to a battery as shown above to the side. What's the charge on the top plate of C1? What is the charge on the top plate of C1? All right, let's go take a look at that one. Poll should be open, so go ahead and answer. I'll start the timer. Go from there. Going through 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, let's end this poll and publish those results and take a look. All right, so the correct answer here is D. Nobody chose A or B, which is really good. A couple people chose C, and then we got D as our correct answer. Let's talk about why. So in this case, we have 2 capacitors acting in series with each other. That means that I can find the total capacitance by using the 1 over, the equivalent capacitance is 1 over the sum of the individual parts, which works out to 2 microfarads of capacitance in the circuit. Plugging that into Q equals V times C, the capacitance equation, solved for Q, I get 9 volts times 2 microfarads gives me 18 microcoulombs of charge on the top plate. And positive, because that's the positive side, we're going to get negative side underneath, and then positive, negative, and then back to the battery. So positive 18 microcoulombs of charge on the top plate is how you would tackle that problem. And again, positive, negative, going through those capacitors in there. All right. Okay, so we've done the capacitors. We've done the basic circuit stuff. Let's talk about probably the second most. It's definitely up there in the top 3 equations dealing with circuits, and that is Kirchhoff's voltage laws. And that is, I'm going to abbreviate them KVL and KCL. These are the basic tools in our toolbox for analyzing and breaking apart circuits. KVL is based on the conservation of energy. All the work that goes into a given charge must be used up by the time we get back. Or in electrical terms, the voltage drop of the components must be equal to the voltage drop of the source. So if we're taking, for example, this loop right here, we're going to start at the battery with the positive terminal. We're going to go through R1, through R2, through R3, and back to the battery. The battery in itself gives us a positive voltage. I'm ignoring the internal resistance of the battery here. You may get a question within in there. Just treat it as a separate resistor. And then as we get to R1, we'll go down a certain amount. Then R2 drops us down even more. R3 takes us back down to 0, which is where we would then go back around to the battery and go from there. We're also assuming in this case that the resistors or the wires have no resistance, which is very common for these questions. The current law is the same sort of thing, except for now we're looking conservation of charge. All the charge going into a junction, conduction of wires, must be the same as the current going out. So in this case, I have I1, I2, I4, and I5 going into this junction, and I6 and I3 coming out. That means that the current going in must equal the current going out. And that's where we get the generic equations for series and parallel circuits. Is based on Kirchhoff's voltage law and Kirchhoff's current law. So that being said, let's try to tackle one of these. This is resistance in series and parallel, but also we're talking about Kirchhoff's laws a little bit here to solve this one. I'm going to open up the poll and let's tackle the third and final multiple choice question for circuits. Okay, so which of the following combinations of 4 ohm resistors would dissipate 24 watts when they are connected to a 12-volt battery? All right, so let's take a look. Let's see how we did. Show those results. Publish the poll. There we go. Publish. There we go. Correct response here should be D. This guy over here is the best, or that arrangement of resistors over there is the best option. Let's talk about why. So I'm going to hide this. I can archive that. Cool. Going through the options here. The first choice, choice A, had 3 resistors in parallel with each other. The equation for equivalent resistance is 1 over R equals 1 over the sum of all the individual ones. This gives me 4/3 ohms for my equivalent resistance. Doing the same for this one, I have parallel and series. So 8 on one side, 4 on the other. So for the entire circuit, 1 over R equals 1 over 4 plus 1 over 8. That's 3 over 8. For this one, 3 in series, simply add them up. That's 12. And this one would be 4 for the series part, plus 1 over 4 plus 1 over 4, which gives me 6 ohms in there. So I've got my resistances for each branch. Then I can use my power equation, P equals V squared over R. Again, I could also use Ohm's law to find the current and stuff like that, but I'm going to stick with power for right now. That tells me the total resistance needs to be 6 ohms. So 12 squared divided by math. Yeah, 12 squared divided by 24 is 6. That's why it's choice D out there. Sorry, my brain turned off there for a second. All right. So circuits, the last chunk of circuit stuff here is RC circuits. That's where you have a resistor and a capacitor in a given circuit. And these typically will show up as free response questions, specifically with graphs and stuff like that in there, because they're wonderful for that. But let's go through. Basically, we have a resistor and a capacitor in a circuit, and typically some sort of switch, which would let us either charge it by connecting it to point A, where current would flow from the battery through the resistor to the capacitor, or discharge it by moving the switch to circuit B, where the current would flow out of the capacitor through the resistor until we've dissipated all that energy. The time it takes to charge or discharge the capacitor depends on the time constant. It's the Greek letter tau, and it's equal to RC for an RC circuit. Okay, let's do the math now. Let's assume that we want to charge this circuit up. So I'm going to make a loop in this circuit. where I'm going from the battery through the resistor, through the capacitor, and back. So I'm making one solid loop. Kirchhoff's voltage law tells me that the voltage from the battery must be equal to the voltage of the resistor plus the voltage of the capacitor. Okay, Kirchhoff's voltage law. Voltage of the battery must be equal. Now we're subbing in R equals V over I, or V equals IR for that, and V equals Q over C for the capacitor. So just subbing in our equations that we've got. Current is dq dt, so now I can get this as a differentiable form. In there, Q over C. Great. We're going to divide by R. We're going to combine our terms. We're going to go through and set our limits of integration. So for time, I'm going to go from 0 to t. That kind of makes sense. For my charge, I'm going to go from uncharged, Q equals 0, all the way up to Q equals Q, and integrate it. And we run through. We get the natural log part here. We get that part. We go through. We hit the exponentials, and then we factor out terms. And we end up with, at the final end, the charge on the capacitor as a function of time equals the capacitance times the voltage of the battery times 1 minus e to the minus t over RC. There is our time factor, our tau, right there, and it's a negative exponential. So if I were to make this be t equals 0, well, hey, this term disappears. Sorry, no, e to the negative 0 is 1, and there is no charge flowing. And then if we were to make it the other way around, we get our infinite thing there. Boils down to these graphs here. We've got our current. We've got our charge graph going up to max. And then basically our generic statements here. At time t equals 0, there is no charge on the capacitor. Our voltage on the capacitor is 0, and our current is the battery divided by the resistor. Pretty straightforward. As t approaches infinity, our Q approaches CVB. Okay, so maximum value. Our capacitor voltage approaches the capacitance of the voltage of the battery, and that means our current is dropping to 0. We are going to trend our current high at the beginning to 0 as time goes on. What that basically boils down to is, at the beginning of time, short times, early on in our circuit, we get to our capacitor acting like a wire. Basically, no resistance, it's going to charge up. As time increases, we get to what's known as the steady state of this circuit. The capacitor is going to act like a broken wire. It's going to break that branch of the circuit or that part of the circuit, and no current is going to flow through it. Okay. Most times for this, we are going to be looking at either doing some qualitative sort of stuff where it's what is the current doing? Is it its maximum? Is it its minimum? Or graphing this sort of stuff. So knowing these graphs, super duper important. They will show up on an RC circuit question, pretty much guaranteed. All right, that being said, let's dive into some FRQs. So this is 2019. This is last year's circuit question, and it definitely involved capacitors and resistors. So let's see how we do with this. 2 minutes for part A. Ready, set, go. All right, halfway done. And again, remember, we're looking for the word derive, which means we better be seeing some mathematical equations here, starting from some basic concept. right, and there is time for part A. All right, so first things first, steady state current means that we are looking for the time when this circuit has been on for a long time. It's been on for a long time, which means we can pretty much ignore this capacitor, because a capacitor that is fully charged, has been connected for a long period of time, breaks the loop of the circuit it's in. So really we have current flowing out of the battery, going through the 2R resistor, going through the R resistor, and back to the battery. So we get simply 2 points for this. Ohm's law, R equals V over I, and plugging in the correct resistance, which in this case, series circuit, one path, add up the R's, I equals V naught over 3R. Okay. So again, steady state. If you miss those terms, steady state, this question becomes a lot harder. So really read through the question. Are we looking at right when the switch is closed or after a long period of time for it? Okay, second part, charge of the capacitor. 2 minutes, ready, set, go. All right, 12, 11, 10, and, we're close enough. We'll just end this a little bit early. Charge on the capacitor. All right, so we are taking the C equals V over Q equation, solving it for Q, and going from there, we are taking the voltage and plugging it into V equals IR to figure out how much voltage drop happened over this resistor. Sorry, this resistor, because that gives us the parallel branch. And because we're able to do that, we realize that this resistor up at the top here must have 2/3 of the voltage. This resistor must have 1/3 of the voltage. And because this resistor is in parallel with the capacitor branch, the capacitor must also have the same voltage drop as that resistor, which is 1/3 V naught. Plug it in, and we get our 1/3 CV naught. And that's part 2. So a point for writing down the equation for capacitance. Again, I can't stress this enough. There are a ton of free points on this test just for writing down the equation, just for copying it from the reference table to your test booklet. Don't leave something blank. Write down something, some equation on there. Anytime it's a derive or define or determine, do those, please, please, please. Free points. All right, next one, energy stored in the capacitor. I promised you we get back to it. Here we are. Let's go with that. Excuse me. All right, here we go. 13, 12, 11, 10. And I'm going to be impatient for time's sake. So jumping ahead here. Let's energy stored in a capacitor. We are pretty much doing any correct equation for the energy stored in a capacitor. I would just steal the energy of a capacitor is 1/2 QV or 1/2 CV squared. This guide also grabbed the V equals Q over C. Plugged them all together, you get Q squared over 2C. It doesn't really matter. We had charge and or voltage from part B. So we already had the answers for charge in part B. We had the voltage in part B. Either one of those will work. And we're just simply plugging them in to get our answer. 1 point for an equation. Again, look at all the free points for just writing down equations. And then voltage there. So this is for the charge version of it. Here's the voltage one. Again, we're just plugging in the voltage with CV squared, and that doesn't involve any other equations or stuff like that. All right, next one. Here we go. We're now opening the switch. So this is, again, reading carefully, right? But do not solve. This will take you a while to solve, so please don't try to do it. Just write down the equation that could be used to solve for charge Q of T on the capacitor as a function of time. All right, and here we go. All right, so for this one, we are looking at the switch being opened. So now our circuit consists of the capacitor, which is fully charged, and is discharging its current through the 2R resistor and the R resistor and back. So we're doing this loop right around here. So I'm going to start with Kirchhoff's voltage law, saying that the voltage of the capacitor must be equal to the voltage of the resistor plus the voltage of the 2R resistor. So made a loop, Kirchhoff's voltage law right there. I will also expand that to now be, hey, voltage of the capacitor is Q over C. So Q as a function of time over charge equals the current, and then we can add the R's together. This is V equals IR. Okay. And then we get to turn this into a differential, because while this equation is correct, they specifically asked for a differential equation, which means I need to get my dq dt stuff going on here. And that simply means I'm taking I and turning it into dq dt. And it would depend on the direction here. Yeah, consistent with the loop equation. So if I had happened to say that VC equals VR plus 2R, that means that my current is going to be the negative because I just tracked these over to the other side. If I went this, it made a different loop for whatever reason, I could get away with positive dq dt. But this is the gist of it. You're getting a point for plugging in a differentiable, and you're getting a point for actually doing Kirchhoff's laws to get your loop equation. But again, do not solve, because we don't need to go through solving this. That's more complicated than we need to. All right, then we get to the next part. Graphs. Again, wherever you see a graph, please, 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 please do not leave that graph blank. Make sure we're attempting to do something with it. In this case, this is part E. We've got calculating the current in the resistor R immediately after the switch is opened, and then graph it. Because of, yeah, I think we're good. So I think 2 minutes for this part should be reasonable. So sketch out a graph and calculate some current. Ready, set, go. All right, almost good with this one. Another 15 seconds or so, and then we will dive into the graphs. All right, and time is up. All right, so let's take a look at this one. We are, again, immediately opening the switch. So we are looping through this small circuit from the capacitor through the resistors and back. So if we're looking at this, we want to use a voltage consistent in part B with I equals V over R. So we found way back when in part B, go back to part B for a second, the voltage on the resistor R, which had to be the same as the voltage of the capacitor. So we knew when the capacitor was fully charged, it was 1/3 V naught. And that means we can plug this back in here. So I can plug in 1/3 V naught. The total resistance of this loop if I'm showing it here in the blue arrow, is 3R because it's a series circuit. So the total current must be V naught divided by 9R, or V naught over 3R, V naught over 9R. So 1 point for using a correct voltage. And again, it just says consistent with your choice in part B. If you guessed in part B and put down some random voltage, okay, use that same random voltage here. And then simply just putting the right resistance in. So again, if you had the wrong voltage or had some crazy number that doesn't even make sense for a voltage, but you divided it by 3R, you still get a point for that. So again, this is a good case of if you're not sure, you can guess and work with that number, and pick a number and work with that and still get points out of this question. All right, so that was single I. The next part was double I. What happens to the current as a function of time in this capacitor? So remember, we are discharging this capacitor. We are taking the voltage and the energy out of the capacitor and running it through the circuit. That means my current needs to start high because we're at its maximum peak, and then we will slowly drop down to be zero current. Okay. And again, does it say, I'm going to read the question again. Yeah, explicitly label the maximum with the numeric value or algebraic expressions as appropriate. So we need to, number one, take whatever answer we put in part E, put that as our starting current. And then we're going to asymptote down using that negative exponential curve until we get on there. So number 1 point for a curve that's concave up because we're starting high and going low, for having a horizontal axis as an asymptote. So even if you have no idea what it starts at, this is again where I say knowing the shapes of the graphs makes a difference. This is a discharging capacitor. The current starts high, goes low, and it's a curve. And for labeling the maximum current with whatever you put in part EI. So realistically, if you know two things about this graph and you just simply, oh, I got to label the maximum. I don't know how to do that. I'm going to make up a number. Label that with the graph. We got a point. A concave up, decreasing curve. There's my other 3 points. You can get full points for this question by simply knowing what the shape of the graph looks like and making up answers for everything else. All right, and the last part, part F. Total amount of energy dissipated in the resistors after the switch is open. So R and 2R greater than, less than, or equal to the total amount of energy we put in the capacitor in part C. Okay, so we'll let this go. We open the switch. We let this run until it's dead. There's no more electricity going through the circuit, but somehow we measured the energies. Is the energy that I lost through those resistors greater than, less than, or equal to the energy that I stored in the capacitor? And justify your answer. It means I better see some explanations, some good logical thinking, or some math to back it up. It can't just be a yes because ... Good luck. All right, cool. Let's go over this one. So this one is interesting because you can actually get two different correct answers for it. And this, again, depends entirely on your justification of your answer. So let's go through this in a little bit of depth here. First off, the obvious answer is they should be equal. Right? We talk about conservation of energy all the time. The energy can't be converted or destroyed, only changed forms. So we had the energy in the capacitor, which was 1/2 CV squared or CV, and it all went through into current through the resistors, which dissipated out. Those should be equal to each other. Okay, that gets you 2 points. Check equal to when you say, yeah, conservation of energy. All of its energy goes through. As long as we don't lose any energy, the only parts will be the two resistors. Okay, that's option 1. Option 2, you can actually get away by saying less than. That, yeah, the resistors dissipated less energy than the capacitor. Well, how does that work? Well, you have to, in your argument, in your justification, saying, hey, the wires that connect these parts have resistance as well. And if they have resistance, that means they're going to cause energy to be lost because that's what resistance does. So 2 different answers. One of them, assuming there's no resistance in the wires, they're equal. Or assuming there is resistance in the wires, the resistors dissipated less energy than the capacitor. All right, cool. All right. This is your next chance here. We're going to take about a 5-minute break. Remember, throw your circuit questions down below in the Q&A, or go run to the bathroom, go get a drink. We are 3 hours in with 2 hours to go. Next up, magnetism. See you guys in 5 minutes. All right, so we got a couple more minutes before I'm going to pick this back up. If you could hop back over to Mentimeter when you get a chance. I'm going to leave this up for a few minutes. And just let's vote on, give me some feedback on circuits. How are we doing on circuit sort of stuff? Keeping in mind, we'll do RL circuits and RLC circuits at the end. So go from there. Ooh. Okay. All right. Well, let's take a look. If we have time at the end, I may come back to circuits because the distribution for a couple of these are kind of might merit a little bit more practice on this. But we'll have at least one more circuit question FRQ coming up at the end when we do inductors. So we may revisit this if we have time on there. But also throw your questions down below in the Q&A if you got anything. And it could even just be, what the heck is an RC circuit? Why do I care? Or what graphs do I need to know about? That sort of stuff. Throw it down there. We will do our best to answer it in there. All right. So recapping, looking at nature, our wonderful outside sort of stuff. We are now 60% of the way through the exam. We have covered 2 out of the 3 multiple choice or free response topics. And we are probably somewhere in the 60-ish percent, almost 70% of the multiple choice questions being in those 3 units. Again, for the most of them, we're looking at electrostatics and circuits as our 2 big topics, with capacitance kind of sprinkled in there for good measure. All right, so yeah, take a breath, digest some food, stay awake. I don't know about you guys, I'm pounding the coffee right now. It is 8 o'clock where I am, and normally I'm old. So I normally go to bed at like 9:30. So this will be like weird. Plus I got to work tomorrow, and you guys got school tomorrow. So while we're waiting, just a couple tips here. Please do not stay up all night tonight studying. Get some good rest, get some sleep, eat a good breakfast tomorrow, and then just do your best on the test. If it helps you to review in short chunks, review short chunks tomorrow morning before you get to the test. But please do not stay up till like 1, 2, 3 in the morning trying to study with this. Your brain will be so tired tomorrow. It will not be happy. And I don't think you'll be happy with the results either. So chunk little bits, but really sleep is probably the best thing you could do for your success on this exam for tomorrow. All right, let's dive in now. We've got our next thing. Yep. Hey, nature sounds, how nice. Okay, so next topic, magnetic fields. Magnetic fields makes up roughly 20-ish% of the multiple choice questions, and it's kind of the foundation for some of the free response sort of stuff. So it's roughly on par with electric circuits, ish sort of thing. So magnetic fields, here we go in a nutshell. We've got our field lines. just like for electric fields, we got magnetic fields, and field lines show where a north pole travels to. So any electric field or magnetic field lines are going to show where a north pole is going, away from the north towards the south. And the shapes are going to look pretty much identical to the electric fields we saw earlier, just again, away from the north towards the south, not positive, negative, north and south. And any charged object will experience a magnetic force due to being near a magnetic field. So that is, if I have electrons or protons flying around, they will experience a force due to the magnetic field. And that force is equal to QV cross B. All right, so let's pause for a second, talk about cross product because we haven't touched on that yet in this stream. Cross product cares about the perpendicular components of the two vectors we care about. So in this case, the magnetic force vector, charge is scalar, velocity is a vector, and magnetic field is a vector. So as long as the velocity and magnetic field are perpendicular to each other, or at least have some perpendicular component, we will feel, or that charged object will experience a magnetic force. Now, we do this with the right-hand rule. Some of your teachers may have taught you left-hand rule. It's going to be pretty much the same as long as you remember this one little caveat. The right-hand rule is for positive charges. If you do it with your left hand, it's for negative charges. Now, I will be honest with my kids. I only teach them the right-hand rule and tell them it's for positive things and negative things go the opposite direction because I don't want them getting confused between which hands to use for which scenarios. For me, it's always a right-hand rule. And the right-hand rule works kind of like this. Your pointer finger gets pointed in the direction of the velocity of the particle. Your middle finger and lower fingers, if you want to. You can do one finger. You could do ring and pinky as well. But they point in the direction of the magnetic field. And your thumb goes in the direction of the force. Okay? And again, this is for a positively charged object. Just going to stress that one more time. For a negative charge, it goes the opposite direction. So the force will be pointing down instead of up. That sort of thing. All right, let's try this with a little multiple choice question here. I'm going to open this poll and give you guys a little bit. This one may take a little bit longer. So I may do like 2 minutes for this, just because getting your hand wrapped around certain things might be important. But let me open up this. So we have a figure above showing the paths of 5 particles as they pass through the region inside a box that contains a uniform magnetic field B directed out of the page. Okay, so our B field is going out of the page. And we want to know which particle out of the 5 going in that box has a positive charge. Okay, that is our task. Which particle has a positive charge? And I'm going to start the timer right now. All right. So that was a minute. I'm going to give you guys a little more time just to finish putting this question together because, again, hand rules and stuff like that make this one a little bit more difficult or confusing. But let me take another, I don't know, 15 seconds or so. Then we'll show the results and we'll talk through this one little by little. All right, so remembering hand rules. Right hand rule. Middle finger goes in the direction of the magnetic field. Pointer goes in the direction of the velocity. Thumb should point in the direction of the force for a positively charged particle. So in our case, our B field is coming out of the page. So your middle finger should be pointing out of the page. Your index finger points in the direction that the charge is traveling, and your thumb should point in the direction of the force. Now, this one's a little bit tricky because we need to remember a little bit of Physics 1 or Physics C mechanics, and that is when you have a force causing you to curve, that force must point towards the center of the curve. So for A, the force needs to be pointing down towards the bottom of the page. B, same sort of deal. C, same deal. D is pointing to the top right corner. And E doesn't look like it has a force on it because it's moving in a straight line. So breaking this down, A and C, I can tell will be the same charge because they are both curving in the same direction when they have the same velocity. So these are both moving up and to the left, and they are both curving, what do I want to say, counterclockwise? Yeah, counterclockwise in there. So they must have the same charge. B and D, if I'm looking at these two must have opposite charges because they are curving different directions as a result of the magnetic field. And of course, E, which wasn't one of your multiple choices, but just in case, E is not curving at all, which means it doesn't have a charge. So E must be neutral. A and C must have the same charge. B and D must have opposite charges. So if I'm going to narrow this down, I'm going to try the right-hand rule on B and on D. Again, middle finger is out of the board. Pointer finger pointing in the direction of the velocity. And we'll see which thumb for those points towards the center of the circle. And it works for B. So B must be positive. D is negative. And then I only know there's one right answer here. So A and C both have to be negative. You can do the same hand rule there. And then E is neutral, not affected at all by the magnetic field. All right, so going back, this was all about doing a little bit of process of elimination, recognizing same curves mean same charge, different curves mean different charge, no curves means no charge, and then applying that right-hand rule to figure out which one has the force point towards the center of the circle. And that will tell you positive charges. All right, carrying on with this a little bit more, then kind of the blending part between physics E&M and physics mech or physics 1 or whatever previous physics course you took deals with magnetic fields and electric fields happening concurrently with each other. So in this case, we need some Newton's law stuff. These questions do not show up super often simply because they do require you to know stuff that is not officially in the physics E&M curriculum. It's in previous versions and stuff like that. But just as we can do this sort of thing by shooting a charged particle through an electric field to give it a velocity, and then through just a plain magnetic field to make it curve in different radii. And the curvature of these radii will depend on the mass of the particle. Okay, so short answer is between the parallel plates, almost always this will be set up so the two forces are equal to each other. The electrostatic force from the positive and negative plates will be equal to the magnetic force from the B field, in this case going out of the page. So QE must equal QVB, and that will let us figure out the velocity of a given particle. So we can kind of select for velocity. If our particle has a greater velocity, it won't make it through because it won't be going in a straight line. If our particle has a slower velocity, it will, again, not be making it through because it won't be moving in a straight line through there. Outside the electric field, we're just in the magnetic field, we can set up Newton's second law, F equals ma, and the only force acting on it is this magnetic force, or QV cross B. Because these are going parallel with the page and the magnetic field is going perpendicular to the page, I know there's already that cross product that's going to be happening there, which is why I didn't write this out as QV cross B. I know they're perpendicular already. I don't need to worry about writing that extra symbol in there. And that equals mv squared over r. We could drop a v and get QB equals mv over r. But the gist is here that this will depend on the mass of the particle, which is why if you're doing anything with like chemistry, this is one way to determine the mass of the charged particles that are going through. This is essentially ion spectroscopy or mass spec or something like that for chemists. So if you're interested in chemistry, this is the theory behind how we figure out the masses of different isotopes and stuff like that. But neither here nor there. We will be possibly asked to do this, but it's unlikely. I'm putting it on because it's a concept that may or may not happen on the test for the second part, but definitely the first part, where you're talking about these two fields must be equal to each other between the parallel plates, could definitely show up on the exam. All right. Okay, so we've got magnetic fields magnetic forces due to static fields, which we use the right-hand rule for, and its magnetic force is QV cross B. Well, if we didn't have enough magnetic forces, we also have magnetic force from a current flowing through a wire. Yay, electricity and magnetism, two sides of the same coin. We are seeing right now that current can cause a magnetic field. In a second or an hour or so, we'll go to magnetic fields can cause current in a wire and flip-flop back. But this one also is a right-hand rule. I tend to call this the right-hand curl rule, just so my students can distinguish it from the right-hand magnetic field rule, but it doesn't really matter. It's the same basic idea. Your thumb goes in the direction of the current. And then if you take your hand and you curl it around the wire that we are trying to conduct or send electricity through, your fingers will point in the direction of the magnetic field lines. So in this case, with an electric current going to the right, magnetic field lines are going to loop in a out of the page above the conductor into the page below the conductor sort of fashion. So this would be dots coming up here and crosses going into the page below. Okay. And the equation for this is magnetic force is the integral of I dl cross B, which more than often, I want to say, like I put a percentage, I'll probably be slightly off. 90% of the time is ILB sine theta, where we're not worried about integrating over tiny chunks of length. We're going to say, okay, give me the whole thing, and just ILB sine theta is more often than not the way you're going to see it or use it in a given question. Okay, so with that being said, let's take a look at one problem using this. Okay, so again, curl direction. We are curling our fingers around the wire to show us magnetic field. Our thumb points in the direction of the current. All right, so we have two straight, long, horizontal lines that are parallel to each other in the plane of the page. Carry electric currents to the right as shown in the figure above. I put a sensor at point P and say, hey, what is the direction of the net or the total magnetic field at point P? Point P is exactly halfway between the two wires. What is the magnetic field going to look like at that spot? All right. Again, 1 minute-ish. Ready, set, go. Oh, hold on. Open the poll. Now ready, set, go. All right. And there is time for that one. This one, I put in 6 choices on the slide. Yes, Vimeo only gives you 4 options. So good job for those of you who figured out it wasn't E or F, but, you know, we'll go with it. Correct answer here is choice D. And the vast majority of you went and chose that. So awesome. Let's walk through how this one works. Okay, so we're going to take the right-hand rule. We're going to apply it to the top wire and to the bottom wire. So for the 20 amp wire, thumb pointing towards the right, fingers curling, we see that the field is going out of the page above the 20 amp. So it's out of the page on this region and into the page in this region. So the 20 amp current producing a magnetic field that is dots above, X's below. The 10 amp current is going to do the same sort of thing. It will be going out of the page in the middle region and into the page below the wire. And now the reason why it's not F, besides the fact I didn't put it on the choices, is that the 20 amp current must make a bigger or stronger magnetic field than the 10 amp current does. Okay? Simply put, magnetic field depends on the current. And the bigger current gives me a bigger magnetic force, a bigger B field in there. So because we have a bigger current, we're going to get more magnetic field from the 20 amp one, which is why the into the page choice wins. If these two currents were identical to each other, then we would have no magnetic field between them, and vice versa. But because the 20 amp one is bigger, it's going to dominate. And that's why the net magnetic field is going into the page at that point. All right. Next choice. And this one's more, again, right-hand rule, practical sort of stuff. This is one that comes up from time to time where they give you 2 wires. And they simply say, okay, we've got current flowing through these wires. What's going to happen? And the short answer is, as long as the currents are going the same direction, those wires will be attracted towards each other. And you may say, okay, well, how does that happen? How do we know that these 2 wires are going to be attracted to each other just because they have current going through them? And here's the gist. We take the right-hand rule. I'm going to apply it for current I1. So I'm going to put my thumb facing towards the top of the screen, curl my fingers around that imaginary wire, and I get that the magnetic field is coming like this, out of the page on the left side, into the page between the 2 wires. Fair enough. So now this wire right here has a field going into the page. Well, into the page with charges moving through this wire, moving through wire 2, means I get to do right-hand rule for magnetic forces. Pointer finger in the velocity, that's towards the top of the page. Middle finger towards B, that's into the page. Hey, my right thumb is now pointing to the left. It's causing a force on wire 2 to move it to the left. The same thing applies on wire 1 from current 2. Current 2 is going into the page on the right side, out of the page on the left side. So we'll get this out of the page going here. Do the same right-hand rule trick. Again, pointer pointing up. Middle fingers are coming out of the page. And that means the force is going to the right. So the wire 1 is being pulled to the right. Wire 2 is being pulled to the left. They're going to attract each other. Okay. Now, if the currents are going opposite directions, one of these gets flipped, and you will see them start being repelled. Actually, they'll both be repelled. They'll both be pushing outwards from each other. So if the currents are going in the same direction, they will both experience a force attracting them to each other because the magnetic field from wire 1 happens to coincide to make a force of attraction, and vice versa. If they are moving in opposite directions, switch the direction of current, both those forces are going to be repelling those wires apart. So same directions, they attract wires. Opposite directions, they repel wires. And again, this can come up as a multiple choice thing. Typically, it's not a free response one, but definitely a multiple choice question dealing with magnetic fields and two wires and the current in it. The current's going the same direction, they attract. Currents going opposite directions, they repel. Okay. So far, we've done it with magnetic fields from pretty much straight wires. But we all know that there are many other shapes that wires can be that aren't straight lines. We can make loops. We can make curls. We can twisty it around and stuff like that. And you might be asked to deal with some sort of magnetic field from a wire that is not a nice straight line. In fact, I'd probably bet money that you're going to have to do at least one question with a wire that is not a nice straight line. And to do that, we're going to use the Biot-Savart law. The Biot-Savart law basically says, okay, we can figure this out. We can figure out, based on these tiny lengths of a wire and the tiny r hat direction, the radius direction term here, it's hat, so it's just a direction vector. With the current flowing through the wire, we can figure out a tiny bit of magnetic field. Mu naught is the permeability of free space. No, magnetic permeability. On your reference tables, it's another constant that will help us determine the magnitude of it. But most of the time, you're just going to have it as a mu naught. Kind of like how epsilon naught has a number on your reference tables. Most of the time, you're going to have just epsilon naught on there. Mu naught will do the same sort of thing. And then r squared, the distance away from our current wire that we are moving. Oh, I didn't actually. Okay, so the gist is here, we break up the wire into tiny sections of length dl, and we cause that to have a small magnetic field. I'm supposed to have a picture here. I don't know where my picture went. That's interesting. Pause 1 second. I will see if I can bring that picture back. That's not the right picture. All right. Scratch that. No picture. Bad teacher. Oh, well. Just want to make sure that that picture wasn't supposed to be something important. I feel like it was. Oh, well. Anyway, it's gone. Okay. Sorry about that. 8:30, brain's turning off. But really, a more practical example of this is Ampere's law. So if we were to take through and go through and integrate all of these wonderful things, we throw an integral on B, we throw an integral on this DL part, we actually end up with something very similar. By very similar, I mean extremely similar to Ampere's law. So Ampere's law is a general case of Biot-Savart. It's not going to be used in every case, but this is a much easier equation to work with to find magnetic field. And basically what it says is this is the magnetic equivalent of Gauss's law. We're going to, in Gauss's law, we created a sphere or a shell or a surface around a charge, and then we were able to integrate over the surface to find the electric flux and figure out the charge enclosed inside. Ampere's law, we're doing the same basic thing. We're going to create, now instead of a sphere, we need a path. And that's basically the distinction here is Ampere's law deals with paths, whereas Gauss's law deals with shells or spheres around it. We then integrate over that path, which is why this is a DL, not a DA, and determine the enclosed current instead of the enclosed charge. And that's simply because a charge will create an electric field, but we need to have a current, a moving charge, in order to create a magnetic field. And that's the big distinction between why this is I and not Q. It's I because we have to make B on there. All right, so this gives us a Ampere's law. And we will probably have to use Ampere's law on an FRQ. It's fairly straight. I won't say guaranteed, but you'll probably see one on there because this is kind of the foundation of electromagnetic induction. Current creating a magnetic field. All right, so one really classic example of that is a solenoid. Right? For a solenoid, we're going to create an Ampere's law path. Again, path, not surface. That is a rectangle. So I'm basically going to look at all the magnetic field lines going into this pink rectangle right here. And we're going to start it inside the solenoid. in a solenoid is nice because it condenses all of the magnetic field lines going in one parallel direction, which is super nice and handy. I don't need to worry about any trig stuff inside the solenoid because they're all parallel going down the center of the solenoid. And we're going to extend it upwards a large distance. How large? Well, large enough that the end of my path is pretty much outside of the magnetic field of the solenoid. So super far, significantly far away. And because the magnetic field lines are perpendicular to the side of the path, so perpendicular here, we really only need to worry about the section here. Because here is the only case where we could have lines entering and not necessarily leaving. So if we're going to do this, let's look at Ampere's law. The integral of BdL equals mu naught I. Okay, well, great. If I integrate over this, the magnetic field inside the solenoid should be pretty constant, which is pretty nice. It shouldn't be changing. All these magnetic field lines are pretty consistent. They're parallel. There's no closer together, farther apart sort of thing. So constant magnetic field. And if I integrate over the entire length of my little path, I will get just L. That's pretty simple. It's a rectangle. And the length would be L in there. Mu naught is our constant. And I enclosed is the amount of current in the solenoid. Well, N in our case is the number of turns. So how many turns are there in my given length? I don't know, but let me make up a new quantity called N, lowercase n, which is the turns density, the number of turns in a given amount of length. So if I take N and divide it by L, I get little n. And I get this equation for the magnetic field of a solenoid, which happens to be right on your reference tables. The magnetic field of a solenoid is mu naught Ni. And when will we be asked to use that? Well, probably any question that's talking about a solenoid would be a good guess. It's really not applicable anywhere else except for a solenoid question. So this is another nice one that you'll know when you have to use it, and you have to use it when we're talking about solenoids, and specifically the magnetic field inside a solenoid. All right, so this chunk, we have 4 different parts for Ampere's law. Coaxial cable consists of a solid inner conductor of radius A, surrounded by a concentric cylindrical tube consisting of inner radius B and outer radius C. The conductors carry equal and opposite currents, I naught, distributed uniformly across their cross sections, and determine the magnitude and direction of the magnetic field at a distance r from our central axis. All right, there are 4 parts to this. I've got a 4-minute timer. I think we're going to go a little bit longer than 4 minutes on this one, just so we can have plenty of time to get this done. I think we'll do maybe like 8 minutes, 2 minutes per part, because this very easily could be an FRQ question. So I'm going to start the timer, but we're going to give it 8 minutes, not 4 minutes for this one. So go through A, B, C, D, tackle these out, and in 8 minutes or so, we will go over them in order. Oh, that's a 5-minute timer too. 8 minutes. I'll go from there. All right, another 3 minutes or so, and then we will go over this one. If you are finishing early, just a reminder, Q&A right below this. Go ahead and throw any questions you have down there. Even if it's not on this topic, anything from previous or future sort of stuff is fine there too. So. All right, so let's go through these and take a look. Let's see how we did. All right, so let's start by looking at part A. Part A, where our radius is less than A, we are less than the radius of this inner coaxial cable. So some fraction of that inner current is enclosed by our path, by our circle we're putting on here. So by the way, our path is a circle because we're just going around the interior part. So I'm going to choose a circular path with a radius r because that would best enclose the area we're looking at caring about. The fraction of current that we are enclosing must be equal to the total current in that inner path or that inner cable multiplied by some fractional part of it. So pi r squared would be the area of our path divided by the total area. So it tells us that we really have r squared over a squared because the pi's cancel out as the current we actually enclose in here. So our magnetic field times the 2 pi r, the length of our path, is equal to mu naught I naught r squared over a squared. And then simplify a little bit, we can drop one of the r's out, and we get mu naught I naught r over 2 pi a squared. And that is for the inner circle where we are inside the inner cable. For part B is a little bit easier. For part B, we are between the two cables, which means we fully enclose the inner cable and we don't touch the outer cable. So I don't even need to worry about fractions of current. I can simply say, hey, I am enclosing the entirety of the current in that inner cable, and I'm still doing a circle because that still fits. Everything's cylindrical, so circles are a great way to go around the outside of a cylinder. So 2 pi r there. So B will be mu naught I naught over 2 pi r. So there is our enclosing everything inside one wire. For C, we do the same sort of thing. C puts us where B is less than R, but C is bigger than R. So we are somewhere inside the outer secondary cable. All right, well, so the current we're enclosing must be equal to, well, first off, all the current on the inner cable, which is, let's call that positive. Why not? Minus, because the currents are going different directions now, minus the current in the outer cable, but only part of it, not the whole thing. So I can do r squared minus b squared to tell me how far in I've gone for this little shell, because we're making kind of like a hoop. We need the inner radius and the outer radius to do our pi r squared sort of stuff. So r squared minus b squared is my inner chunk of the outer cable. Yeah, the inner chunk of the outer cable. And this is the total outer cable areas. And then we can, or the hoops and stuff, the pi's cancel, stuff like that. So we're left with this fraction of our total current. Again, minus sign here because the currents are moving in opposite directions. If they're moving the same direction, we make that a plus. And here we just simply go through and do the math out. I'm not even going to bother simplifying or distributing anything through here. It can all stay on the outside, but just leave it. Again, we're making a circular path. So we're getting 2 pi r. Again, and our enclosed stuff is, that sort of stuff to get mu naught I naught over 2 pi r times this wonderful fraction. And then we get to part D. Part D is my favorite part of all these because it involves no math on my part. In part D, we enclose everything. The question told us that we had equal and opposite currents through the cross sections, and they will simply cancel each other out. So if the total currents in there, positive and negative currents cancel out, there must be zero current, which means there's zero magnetic field, which is my favorite kind of question to work through. Easy, 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 easy. All right, so that is Ampere's law. Let me see what we got coming next here. I think it is. Is it? Where am I? Oh, yes. All right, so that is Ampere's law, current in a wire. We then get to the next chunk, which is Faraday's law. And Faraday's law is the first and probably the most important law of electromagnetic induction. We've seen in the past with Ampere's law, current causes magnetic fields. We have seen magnetic or charged particles cause magnetic forces. And here we're going to take this kind of the final step here and say simply that electric fields, voltages, potential differences in a wire induced can be caused by a magnetic flux. A changing magnetic flux will create an electric field and therefore an electric current in there. And we can see in the little demo here, some of you guys may have done this FET lab, but this is one where you can simply just take a magnet, you wiggle it through a loop of wire, and you can notice the light bulb turning on. And the brightness of the light bulb depends on a couple things. It depends on how fast we move the magnet through, which is the flux. How much of this flux are we changing? It also would depend on the strength of the magnet and the number of loops, which I'm not controlling in this little GIF, but it's there, or GIF. Yeah, not GIF, GIF. In here, basically, a moving magnet can create electrical current. That's the gist of Faraday's law. Okay, so Faraday's law simply says that we can create induced current, induced voltage from magnetic flux. Well, magnetic flux, what the heck is that? Magnetic flux is the integral of the magnetic field dotted with the area or the changing area vector. Dot, again, remember cosine theta for a dot product. So BA cosine theta is another way to write this equation out. And there are three main ways we can change the flux for magnetic stuff. Number one, we can change the magnetic field. I can change B. Okay? And that was what we were seeing in the little simulation. I am moving the magnet back and forth. That is changing where the magnetic field lines are. That changes the magnetic flux. I can also change the area. So if I can imagine taking that wire and squishing it or stretching it or having it be a rectangle that I could elongate or compress, that would change the area of this. And we can see this in this middle picture. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 X's, 14 magnetic field lines going through the circle in the picture on the left. And once I stretch it, I have 2, 4, 6, maybe 7 in there. So by stretching it, I have decreased the amount of magnetic field lines going through that loop, which is decreasing the flux. And the final part is changing the angle between the magnetic field vector and the area vector. So if I start off with everything being perpendicular, and then we switch it so it goes to parallel, we are changing the flux based on that, or changing the coil. Sorry, the coil where, yeah, this picture is not the best, but basically the area vector and the coil vector are going the same direction, or the magnetic field vector and the coil are going the same direction. Here we make it less, so there's less of the blue area, and then when we make it completely perpendicular between the area vector and the magnetic field lines, there is no flux going on in this one, so we can change the angle as well. Out of those three, the ones that you're going to see most common, changing the area and changing the magnetic field, are ones that I've seen show up on FRQs and probably MCQs too in the past. All right, last part of the laws is Lenz's law. Lenz's law simply tells us what's the deal with that negative sign. If I go back to Faraday's law, it has this wonderful little negative thing floating around here. And why? Why am I worried about negative things? What does that mean? Well, it simply means that in Lenz's law, it tells us the direction of the induced EMF. And so the short answer is that negative sign means the induced EMF in a wire will always try to oppose the change in magnetic flux that caused it. So if I have a EMF that wants to cause the wire in the current to flow, a magnetic field that's going to try to cause the wire in the current to go in a counterclockwise direction, the induced current will be in a clockwise direction. It will be always the opposite to try to stop the change that caused it. Okay, and that is Lenz's law. So, for example, a wire is moving to the right along two parallel rails in the presence of an external magnetic field. So I have a magnetic field here. This is going into the page because of the X's. We want to find the induced electromagnetic, or EMF, the electromotive force, the electromagnetic field, but either way, they both work for that. So what we've got is this wire moving to the right. As this wire moves, we are making this loop get bigger, and we are increasing the area of that loop. Okay? That wire is moving at a set speed. V equals delta x over delta t, dx dt, the basic physics, probably first equation you ever learned in physics. The area that's changing is equal to the length of the pole times delta x, the change in area here, or length of this, change of position of this pole. There we go. So if we want to figure this out, we can look at our equation. Induced EMF is the change in flux over the change in time. That's negative because of the direction, because we're always going to oppose it. The flux is B times A. Well, we know B is constant because there's nothing here that's changing the magnetic field. It's a constant thing, but the area of this loop is changing. So how do we find the area? We said it was L delta X. So B is a constant, L is a constant. We're not changing it this way. And then dx dt, well, dx dt is just velocity. So the induced EMF here is negative BLV. And if we want to figure out the direction that it's going, we can use some right-hand rules, because why not? First one tells us which way this is going to move. I have magnetic field vector going into the page. velocity going to the right, that tells me that the force is moving upwards. This is a slightly different right-hand rule than one we did before. It's the same basic idea in there. And then we can use the loop rule to say, hey, we've got an increasing flux because my area is increasing. I've got to oppose that. Opposing it means I better get a magnetic field that is going the opposite direction. So because I have the field going into the page in this top picture, the induced field must be coming out of the page. Yeah, out of the page, which will oppose, try to reduce, try to lessen the increasing flux inside this loop. And if the field inside the page is coming out of the loop, we can use our curl rule. If my fingers are going into the page on the top and out of the page inside the loop, that means the current must be going in a clockwise direction. No, counterclockwise direction. Counterclockwise direction, going this way, to the left, down, to the right, and up, going through here, because that would produce the induced magnetic field that would oppose the existing magnetic field's increasing flux. That's a lot of words, but I hope they came across okay. We're increasing the area here, which means we are increasing the flux of this loop. To reduce it, we need to create a magnetic field that is going to reduce the flux in here, which means it must be pointing the opposite direction. So in this case, the B field is going into the page, and going into the page results in a right-hand rule telling us that the current is flowing in a counterclockwise direction. And how much current is it? Well, we can figure that out by using this one. And if we divide this by R, we've got the current. So BLV over R would tell us the current. BLV would give us the potential difference. And we can go from there to find everything else we could ever dream of finding because of that. All right, enough of me rambling. Let's do a practice question. All right, a circular loop of wire has a resistance of 30 ohms, an area of 3 square meters, and is fixed in place, cannot move. We project a magnetic field into the page around the ring. What would the rate of change of the magnetic field be in order to produce a 1 milliamp current in the ring? All right, let's start, and then I will open the poll in a little bit. I'm going to let you guys try to figure this one out before we get to opening the poll and eliminating an answer. All right, poll is opening right now. All right, and there is time. I'm going to let you guys put your votes in a little bit more as we go through. So I'll leave this open for a little bit longer. Throw your votes in the poll, then we will publish the results and see how we did. All right, let's take a look. So, there we go. Correct response here should be D. If you had E, my apologies. I kind of eliminated that one for you right away. But D is the right answer. We're kind of split between D and C. So let's kind of work through this one a little bit more and see why D is the right answer and C is not. All right. So first things first. I'm going to look for what voltage do I need? What EMF do I need to induce in order to make a 1 milliamp current go through here? So using Ohm's law, R equals V over I, V equals IR, we get that we have 30 ohms because we're told it's 30 ohms, And 1 milliamp means I need to get 30 millivolts of current going through here. Or sorry, 30 millivolts of potential difference in this ring. Okay, well, I know by EMF, my voltage is the flux over time. And that must be the, dBA over dt. A is constant. They tell me that this cannot move. It's fixed in place. So that must mean that dB dt is changing. And dB dt is the constant rate of change of the magnetic field. That's what I'm looking for, is this dB dt part. So dividing by A, V divided by A is dB dt. 30 millivolts divided by 3 meters squared. This is 30 times 10 to the negative third divided by 3. So that's 1 times 10 to the negative second, which is choice D in there. 30 times 10 to the negative third. Yeah, so it's, I can see where C came in because we have the 3 here, but 30 divided by 3 will cancel out that 3 and we're left with the 1 on there. And then the other part might have just been millivolts and confusing that with something else. I'm not quite sure. But that is the options for that one. So Ohm's law, then Ampere's law, and then solve and go. All right. Yeah, we are right about here. Cool. We are getting pretty close to the end of the content, which is awesome. And then we'll spend the rest of our time doing more free response questions or Q&A or whatever you guys feel the urge that we need to do. So again, throw those questions down below. If there's something you want me to go back and focus on, let us know down in the comments, and then we'll do it. All right, the last chunk here is about inductors and RL circuits. So an inductor is simply a coil of wire that is wrapped around a core, and it's used to smooth out spikes of current. That's kind of its job in there. And basically, we take Faraday's law, d psi b over dt, and we're going to set that equal to L di dt, where L is the inductance of our inductor, and di dt obviously is the change in current over time. This is, again, smooshed on your reference table. We are down here, epsilon equals L di dt with the negative. So really, these two equations right here are pretty much the same. Just extend them further on. They just didn't fit on one line. And then the energy stored in an inductor, I'm not going to bother deriving it. Here it is right here. It's 1/2 Li squared. And I don't think you're ever going to be asked to derive it. It's just going to be here. Here it is. Use it. Go from there. So the energy in an inductor, 1/2 Li squared. And that lets us make RL circuits. RL circuits are pretty much exactly like RC circuits, except for one or two kind of different. I think one major difference on there. You're going to get the same sort of equations for it. So the voltage in the inductor is the battery voltage times 1 minus e to the minus RT over L. And same deal with the current. We just simply divide those by R, and then we're good. The time constant here is R over L instead of RC. So I guess that's one difference. L over R, because it's tau needs to be in the denominator. So we get our time constant to be slightly different. The shapes of the curves look very, very, very similar. The only difference here is if we're noticing what's on these graphs, they are the opposites of what a capacitor is. A capacitor starts off with no voltage and goes up to high voltage, and high current goes down to no current. An inductor starts off with no current, goes up to high current, and high voltage down to low voltage. And if we were to put it in simple terms, a steady state inductor is going to act like a wire. It will be just a plain, boring wire. You will not tell the difference that is there after the switch has been closed for a long period of time. When the switch closes for the first time, that instant where you close the switch, the inductor is going to act like a broken wire. It's going to try to stop all the current from flowing through this circuit. And it will create an opposing current to try to stop that from happening. And then over time, that induced current will get less and less and less until that magnetic field is, or the changing magnetic flux is gone, and we are allowed to just go through a normal circuit. Okay, so capacitors start like a wire, end like broken. Inductors start like broken, end like a wire. Okay, so kind of the opposite things. And the graphs will be the same shapes, just opposites of each other. So I for capacitor looks like V for inductor. I for inductor looks like V for capacitor. Yeah, that's how I said it. So just mirror those two things together. They're going to be very, very, very similar shapes. Just inductors let current go through at the end, and capacitors let current go through at the beginning. And that's the big difference between them. Like capacitors, I'm not expecting for you guys to have to derive these equations. You might, but it's unlikely that you're going to have to do it. I will expect you guys to have to interpret the graphs and the circuits involving them. So that being said, let's dive into a FRQ. This is our circuit one. Said there was another one coming. Here's another circuit one for RLC circuits. So ready, set, go. Let's dive in. Here is part A and part B. So 2 parts on here. I set a 2-minute timer. We're going to make it 4 minutes. So you've got 2 minutes apiece, A and B. Here's our circuit. We've got the switch S initially open. The capacitor is uncharged. There's nothing in the capacitor. And we have a voltmeter to measure the potential difference across R1. Actually, you know what? No, because A is so simple. You know, let's do, no, I said 4 minutes. Let's do a certain amount of time. And when I think it's enough, we'll come back. I'll set a 2-minute timer. We'll probably go over that for A and B. But here we go. Do your best, scratch paper, and get those done. All right, so there's 2 minutes. Looking really quick at some of the questions that were asked right below here. Can we go back through the voltage current through the parallel series resistors and capacitors? Yeah, definitely, we can hit that again. Part of that's going to be happening here, but yeah, we can definitely go back and hit that again. And then when do we use each law for magnetism? We will briefly go over those as well. So let's knock this one out first here, and then we'll go to the next part. So first off, looking at this circuit, I see we've got a 20-volt battery or 20-volt EMF battery. There may be an internal resistance in there. We don't care because we're told the overall thing here. Has to go through a 10-ohm resistor. Then we get the switches and back around. If I wanted to draw a voltmeter for measuring R1, voltmeter has to be, and this is the wonderful part about these, is they will always tell you how you connect them. Voltmeters need to measure stuff across resistor R1. So I will draw it across resistor R1. And the symbol for that is V. Am I going to expect this to show up on a test? Probably not, because I don't think they give you those symbols. But this is an old question. It's from before 2000. But it's possible in there. All right, part B, at time t equals 0, we move the switch to position A. Determine the voltmeter reading, so R1, for the time immediately after t equals 0. So we have this circuit going from the battery through R1, through our uncharged capacitor, through R2, and back to the battery. All right, so immediately after the switch is closed, capacitors act like a wire, which means I ignore this. This doesn't matter at all. And I would have a 20-volt EMF, 10, 20, 30 ohms of resistance. So resistors in series, we add them up. So R1 plus R2 and back. So we will end up with, oh, look, Ohm's law, 20 volts over 30 amps, 2/3 A, and that means we are 6.67 volts going through there. Or you could also say something like, hey, this resistor is twice as big. It must take 2/3 of the voltage. This resistor must take 1/3 of the voltage. Because they are in a series circuit, they must have the same current, and et cetera, et cetera. So yeah, this one, really, really interesting. I'm not sure why you're getting 2 points for drawing a V in a circle here. Again, this is an older question, but I guess what this tells me is, hey, if we're going to draw something, let's draw it. Don't leave it blank. I mean, if it's 2 points for doing basically nothing, take those points and run with them. All right, and part B, Ohm's law. So writing out R equals V over I or something like that for finding the right current and for finding the correct voltage on the 3 points. So again, 5 out of 15 for doing a little sketch and some other stuff. That's not bad at all. All right, so now we are at a long time. We've reached steady state current. We're again going to measure the potential difference across R1. Determine for this later time each of the following. What's the voltmeter reading? What's the charge on the capacitor? All right, ready, set, go. All right, and we are just about out of time for part C. All right, cool. And done. All right, so let's take a look at this. Long time, again, our switch is still at position A, so we still have this switch closed. And after a long time, this capacitor will reach the same exact EMF or same exact voltage as the battery, which means no current will be flowing through that loop. And if no current flows through the loop, that means that the voltage on this resistor, which would be V equals IR, would be 0 because there's no current flowing through it. So I would have 0 volts on R1. For the capacitor, again, steady state means that it must have the same voltage as the battery, so we know it's 20 volts. We also are given the capacitance for this, so we can simply just use Q equals CV and plug it in and solve, and that gets you 1 point. So 2 points for recognizing that the capacitor acts like a broken circuit or breaks the circuit after a long period of time, and that means no current runs, so you get V equals 0. And then 1 point for simply plugging and chugging in the Q equals CV equation. All right, next one. Now, let's look at the inductor. Okay, so this is the second half of this. We've kind of done the capacitor sort of thing. We're now taking the switch and moving it to position B, connecting these parts. So our circuit is battery, resistor, inductor, resistor, battery. Okay, determine the voltmeter reading for the time right after we close the switch to point B. All right, 2 minutes, which might be overkill, but go for it. All right. So we've got, in this case, our circuit going from our battery, resistor, inductor, resistor, back to the battery. So we want to find the voltmeter reading in here. Well, here's where we need to remember. Inductors, right when you close the switch, what happens? They stop the current from flowing. So they're going to act just like a broken circuit. So this will be a giant break in the circuit. There's no way you can get through, so there's no current flowing. No current flowing means there's no voltage drop across R1 because it's not a complete circuit. So again, 2 points. I really hope you guys get a question like this one, because simply knowing broken, not broken is getting a ton of points in this question. 2 points for simply saying V equals 0 because there is no current flowing through this loop. And because there's no current flowing, V equals IR gives you 0. Okay, next part. E, 2 parts to this one. E single I, E double I. So after a long time, so I've closed the switch to part B, a long time later, the current in R1 reaches a constant final value IF. What is IF and how much energy is stored in the inductor? All right, 2 minutes, Maybe a bit longer because it's 2 parts, but we'll see how long 2 minutes takes. Ready, set, go. All right, and that is it for EI. So, or E and E double I. So let's go through this. A long time after we have this circuit going through with the inductor, after a long time, the inductor acts like a wire and will not stop any current from flowing through it, which means we again have this situation where we just have a series circuit, one loop with 10 ohms, 30 ohms of resistance. So really, this is exactly the same part as, where is it? Yeah, part B. Exactly the same work as part B, except for we're asked to find the current instead of the resistance. So we can simply say, okay, we got Ohm's law. We're still doing this. So battery voltage, 20 volts divided by the total resistance of our circuit. It's the series circuit, so we add them up. 10 plus 20 gives me 30 ohms, or 2/3 of an amp. And done. 20 volts over 10 ohms. I'm not sure why they're giving you 1. Oh, because if you just did one resistor and not two of them, apparently you get half the points for that. So good to know. But let's get the full points. Let's get the total resistance going on there. And double I, this is simply just one point. You take the equation off your reference tables for energy in inductor. UL equals 1/2 Li squared. You have I from part I. L is given to you. 2 henries is given to you in the problem. And then plug it in, and you get 0.444 joules. And apparently, if you use the wrong current in EI, anything except for 0 would get you 1 point for that. So you still get perfect points, even if you screwed up this. As long as you didn't put 0, you'd be fine. All right, cool. So at this point, that is it for content. Let me do another quick poll here and see how we're feeling about magnetic fields and stuff like that. And then that'll kind of dictate what direction we go for the last half an hour, 25 minutes, stuff like that. So fill this one out. And then again, if you want to leave comments down below too about things that you'd like to answer and we haven't answered yet, or areas you want me to double back to, please do that. I'll leave a couple minutes for this to happen, and then we'll figure out our game plan. Okay. All right. So we're kind of bouncing around a little bit with magnetic stuff, but that's okay. So it looks like Ampere's law, Faraday's law, a little bit on EMI, maybe a little bit more. We go over those slides again. And then some circuit stuff again. Okay. Sounds good. So I will re-hit those. I forget. This is another Gauss's law. Yeah. Okay. All right. Any other questions coming through? Let's see. When will V equal 0 in this problem? I'm going to guess that you're talking about this one because it came in a couple minutes ago. When will V equal 0 in this problem? I guess it depends on which V you're talking about. So the voltage drop across either one of these two resistors will equal 0 whenever there is no current flowing through them. And that happens either when the capacitor is in its steady state or its final conditions after a long period of time with the switch closed to A, or when the switch is closed to B and the inductor is in its initial state when the switch just closes. Those would be the times when the voltage across the resistors would equal 0. Other options, because it wasn't super specific, the voltage across the inductor will be 0 at steady state conditions. After a long period of time, where after the magnetic flux has weakened and broken down, the inductor will have no voltage drop across it. At the beginning, it's super high. At the end, the inductor has no voltage. The capacitor is just the opposite. The voltage across the capacitor will be 0 as soon as we flip the switch, and then grow up to the battery's EMF after a long period of time. So hopefully that kind of clarifies the V sort of thing. Resistors have 0 voltage whenever there's 0 current. Inductors have 0 voltage after a long period of time. Uncharged capacitors will have 0 voltage right at the beginning. Okay. So there was a question about magnetic laws and would we use them. So let me jump back to that. So we have several magnetic laws to go through, I guess. I mean, we've got magnetic fields. This applies all the time. So if you're talking about a particle with charge that is moving, we use Fm equals QVB with the right-hand rule and stuff like that. If we get a case where we have current in a wire, that's ILB sine theta and curly hand right-hand rule. If we get a case where we're talking about a wire that is not a straight line, and if you want to see more examples about this, I'm pretty sure I wrote up a couple in the 5-able study guide, linked somewhere on here, I'm sure, for magnetism unit. I'm pretty sure I went through Biot-Savart law and did a couple of examples with different shapes of wire and stuff like that. Ampere's law is my go-to for any sort of what's the magnetic field caused by this current. So if you're given a current and asked about a magnetic field, or if you're given a magnetic field and asked about a current, this could be one of your go-tos. Click through, click through, click through. Faraday's law is all about flux. So if we're talking about a changing magnetic field and talking about a voltage being induced or a current being induced, Faraday's law is where I'm going for that. That is definitely the one that I'm going to jump into for that. Yeah, in a case like this, we have a changing magnetic flux. We're doing Faraday's law. Even though there would be a current going through the wire and stuff like that, Faraday's law is what we're going to hit here because we're talking about a changing magnetic flux. Or they will mention the words induced EMF or induced current or induced fill in the blank. Typically, that's Faraday's law. And I think that's it. That was RL circuits. Yeah. So really, your magnetic laws are pretty straightforward. Maybe not super straightforward, but at least it's the way I think about it. If it's a particle, I'm using QV cross B, right-hand rule. If it's a wire, I'm using ILB sine theta, right-hand rule. If it's a magnetic field caused by a current, or magnetic field caused by a current, and I want to get a number for it, not just a direction, or not just a force from it, but actually the B field for it, that's Ampere's law. If I am asked about induced anything, I'm doing Faraday's law for that. So hopefully that helps get through those. So there are the different magnetism laws and when we use them and why we use them, sort of, kind of. All right. Here we go. Let's go back to Mentimeter. I'm going to just open up one of the questions I had earlier that we didn't answer. Okay. So here we go. What is one topic you hope to cover today? I do have one more FRQ that we have time to go through, but go ahead and put some responses in there and see if there's anything that we haven't done a ton of already that you're not satisfied in. Just go ahead and add more to here, and we will do some more recaps of those things as well. So reading through some questions here. ILB is the magnetic force affecting a wire. Yes. Where are we here? Magnetic force is ILB sine theta. So the magnetic force caused by current in a wire is ILB sine theta. Not to be confused with magnetic force caused by a moving particle is QV cross B. So yeah, those are both talking about magnetic forces, whereas the laws later on are talking about magnetic fields. So forces versus fields going through there. All right, let's take a look at Mentimeter here. Electric potential energy, RLC circuits. Okay. Yeah. Circuit with 2 capacitors and no battery. Oh, so like charging a capacitor. Okay, using a charged capacitor like a battery. Okay, we can hit on those a little bit. Gauss's law. Okay, I've got one for Gauss's law. We'll definitely do. If we got time, Gauss's law again. Cool. Okay, so 2 for Gauss's law. We'll hit a little bit on potential energy, I think. Circuit with 2 capacitors and no battery, RLC circuits. Okay, got it. So since we've got it here, let's do RLC circuits real quick. Again, for RLC circuits, I'm going to make it very, very, very simple. And that simply is we need to remember this slide where inductors at the beginning stop the current from flowing. Inductors after a long period of time act like a wire. Capacitors, can I go to a given slide? Doesn't look like I can. It's a lot of clicking. Oh, there we go. Okay, cool. So capacitors after a long period of time will, no, in the circuit part. There you go. So capacitors after a long period of time will act like a broken wire. In the beginning, they will act like a perfectly normal wire. Okay, and really an RLC circuit and stuff like that is just have those components doing different things at different times. And just like the last FRQ we went through, it will go through the capacitors charging. Okay, great. That means it's acting like a wire at the beginning and then transitioning to stopping all the current flowing through that branch. Inductor does the exact opposite sort of stuff. A circuit with 2 capacitors is going to act very similar to a just plain battery circuit. Let's see if I can find that multiple choice question we did on this. Okay, so like this one, for example, if I take the battery out and let's say I replace it with a resistor and just have 2 capacitors, one of those capacitors is going to have to be charging or discharging. And really, a lot of the questions in there will be similar veins. That one might ask you to make some graphs because you're going to be draining the battery or draining the capacitor to charge the other one. But capacitors in series or parallel, that's where we can get our equations off our reference table. Depending on how they're connected, we can hook them up in series like this. We can hook them up in parallel where we just add the capacitors together. And pretty much all your questions are going to be something along the lines of what happens to the voltage in capacitor 1 if ... or what happens to the voltage across a resistor ... Most of the capacitor questions we're seeing will be like the ones we've gone through already, where it's going to be, here's a capacitor, we're going to charge it, what's the current in it, what's the voltage in it, maybe what's the energy in it, doing, yeah, brain turn on, doing the energy stored in a capacitor, 1/2 QB squared and stuff like that, or 1/2 QB, 1/2 CB squared. Those sort of things are typically what the capacitors are. And you can definitely replace a battery in any of these circuits with a capacitor, and it will behave pretty much similar. You'll just have the capacitor graphs and stuff like that go through. All right. Electric potential energy and Gauss's law. Okay, so let's go to my last FRQ question here, which is this one. Okay, so let's do some Gauss's law stuff. This is, again, from 2019. So this is this last year's, the last set of FRQs that came out, doing Gauss's law with a non-conducting hollow sphere. So we've done one that was conducting and said, hey, all the charge was on the outside. Great, wonderful, whatever. Given a given charge density, so how much charge is there in a smidgen of this sphere? Let's go through this. So the charge density is given as a function of radius. So there's no charge inside 0.03. There's no charge outside of 0.05. And in between, we have B over R, where B is this constant of coulombs per meter squared. So many coulombs per meter squared as divided by the radius is the amount of charge that is in there. So we want to find the total charge of the sphere. All right, well, that just sounds to me like we're just kind of using this charge density and crunching some numbers with radii. It doesn't sound like it's anything super difficult. Yeah, so we're taking the total charge must be the integral of the charge density as a function of volume. So because it's a charge density and it's per meter squared, that's why we've got this thing. Notice they're not putting units in, which is okay right now. I would love to see units in here, but that's okay. So we need to integrate basically over the entire volume with the density of the charge density to figure out the total charge. We plug in what we know. We were given B, we're told R, and the total volume, 4 pi r squared, dr. So volume is area dr, surface area dr. So we can go that way. And we put the proper limits of integration on. So we can pull the 4 pi out, we can pull the B value out, and we get R squared over R, which is just R. R dr, evaluated, go through, and we end up with the current. So a little bit of calculus here. 3 points. 1 point for writing down the simple fact we need to integrate stuff. Again, math points are nice. Putting the correct stuff plugged in. So getting dV from this chunk. Again, we got volumes and stuff like that on our reference tables. So volumes of a, what shape are we looking at? Sphere. Hollow sphere of inner radius. Yeah, so hollow sphere. And we're looking for this chunk right here, which is why we need to integrate it because it's not solid. And then we go through and get our current. Again, this is a great point to make here. If we screw up the current for whatever reason, we can still go on and get points for this question. Even if you have no idea how to do this part, write down a current, or sorry, current, write down a charge, and then go on to the next part, because you can grab those points back if you use this number correctly in future parts. All right, part B. Here's the Gauss's law part. I'm going to let you guys practice here. Calculate the magnitude of the electric field E at the outer surface of the sphere. All right, I'll give you 2 minutes. Crank through this one with Gauss's law. We'll go over it in 2 minutes. All right, and that's 2 minutes-ish for this one. Again, that's roughly the time pace we need to be on to get this done in 15 minutes. So Gauss's law, we're going to calculate stuff. Let's jump right in. Gauss's law, I'm betting we're getting a point for Gauss's law. Hey, there we go. We get a point for writing down Gauss's law and putting the right area in here. So because this is a sphere, we want to use a sphere to encompass it as well. And the surface area of a sphere is 4 pi r squared. So that's where the A comes from in there. So E dot dA, 4 pi r squared times E. Okay, great. A point for correctly substituting your answer for part A into the equation. So whatever our answer for part A was, we put it in as Q, and we pick the correct radius in the equation up there. So because we are now looking for the outer surface of the sphere, we're plugging in 0.05. That seems pretty straightforward. And then we crunch the numbers and do the math. And we got to have correct units on this. So electric field, newtons per coulomb is our unit of choice. But it seems like we can get full points for part B by doing basically nothing for part A, which is kind of how it's going to run anytime they ask you for a number. Like I said before, if you get it wrong, just use that number correctly in the next problem. They will not penalize you for it again. Okay, so that was Gauss's law to find the total charge and the E field, or we found the total charge, then we got the E field. All right, let's do some graphing, because again, we will never leave a graph blank on this exam. Never, never, never. Always fill it out. All right, so 2 minutes on this one. Let's go through and figure out the E field as a function of distance. And I'm going to check Mentimeter again to see if there's anything else on there. So apologies for the screen changing for a second here. Okay, let's go. All right, 1 more minute. If we haven't thought of something, this is the time to think about, okay, what would I draw in if I had no clue what should go in there? All right, so let's take a look at this. Looking for the E field as a function of distance from the center of the sphere. All right, so remember, our knowledge of Gauss's law says that the electric field must depend on the enclosed charge that we are encompassing with our sphere as we go from the center all the way outwards. So the question pretty much has told us that in the inner part of the sphere, there is no charge density. No charge density means no charge, which means we should start off by saying, hey, there's no charge up until we hit this 0.3 meter or 0.03 meters. Once we get into here, we're going to get steadily increasing amounts of charge, because as my radius increases, I will gain more and more and more and more charge inside this sphere until I reach 0.05 meters. After that, I now have enclosed the entirety of the charge. 0.05 meters should be my maximum amount of charge. And then we're going to go with the electric fields as KQ over R and start treating this as more of a point charge and watching the 1 over R progression. So that's a lot of words to simply say, hey, it should look kind of like this. No charge until we reach 0.03. Growing, plateauing until we get to maximum charge, fully enclosed everything, and then a 1 over R sort of progression down towards 0 at an infinite distance away. Okay, so 1 point for simply reading what the question said and saying, hey, we have no charge. That means we have no E field, 0. Gets you 1 point. Okay, starts at 0, concave down, goes up higher. 1 point. Decrease with an asymptote down here, 1 point. All right. And now somebody's going to ask, why doesn't this one become concave up? Simply because if we think about how much volume or how much area of the sphere we are enclosing, we're going to start off, when we first get in here, we're going to get a lot of area, a lot of charge in this. And as our radius gets bigger and bigger and bigger, eventually we get to the point where we're only adding a little smidgen of charge on the outside. So if it were to be concave up, that would mean we add a little bit at the beginning and a lot at the end. And that's not how we're looking at changing the circle radius here. We start with getting a lot as I change my radius, and then it becomes fairly insignificant because most of it is already enclosed. So a concave down sort of graph and then asymptote out. All right. Yeah, now we've got electric potential at the outer surface of the sphere. This one, you know what? I think we got time. Let's crunch through this one. Oh, not with the answers. Let's crunch through this problem because V is very similar to some of the other concepts that we kind of had struggles with and wanted more practice on. So let me run through this one. 2 minutes to tackle this. We'll go over it. We'll do the last part, and then we'll do some final thoughts. We can go. Get ready to ace this test tomorrow. Or maybe not ace it, just do our best at it. All right. Another 15 seconds or so, and then we will go over this one. All right, and there we go. So going back, electric potential, V at the outer surface of the sphere. We're going to assume it to be 0 at infinity. All right, let's walk through some answers here. So first part is we will look at V being, KQ over R, or 1 over 4 pi epsilon naught Q over R. And basically, we had a point for using the right charge, whatever we got for part A. We get 1 point for putting the right distance in because they want the outer sphere. Wow, they're being really generous with this plug-in, this R. We've gotten like 2 points so far simply for choosing the right radius based on the picture. I'll take it. So we've got K off our reference tables, or 1 over 4 pi epsilon naught, depending on your preference. We've got Q from part A. We got R from the picture, and we get our V. Works for me. Or we could do the integral version, which is the same basic stuff. V at R minus V at infinity. V at infinity is 0, so that doesn't matter. Negative EDR. We got E from part B, and put our equation in there and put your limits in, do your integration. Hey, we get the same thing there. So there is part D done. Personally, I like the non-calc way of doing this, but if calc is what jumps into your mind when you think of this, then do it. Whichever way is going to be best for you. All right, and the last question here. Well, I'll just go over this one without giving time because we got 5 minutes left. Woohoo! So we're releasing a proton from rest at the outer surface of the sphere at time t equals 0. So I'm going to put a proton right here. It is going to be repelled because the sphere is positive and the proton is positive. So it will be pushed away forever and ever and ever. Maybe not forever and ever and ever, but it'll go flying away. Calculate the initial acceleration of the proton and the speed of the proton after a long period of time. All right, so first part, Newton's laws. So we do need to have some Newton's second law stuff going on here. That's F equals ma. The force is Q times E. Taking the electric field strength equation, solving it for force, and plugging in it equal to ma, and you get A equals QE over M. We can't do this with KQQ over R squared because we can't treat the sphere as a point when we're right on the surface of it. The sphere is much bigger than the proton, so it can't be a point at that time. But we do know what the electric field strength is, so let's use that. All right, and then we get Q, charge of a proton, 1.6 times 10 to the negative 19th coulombs, times E, right there, which we already calculated, over M. And I'm pretty sure M is on the front page of your reference tables. I should double check that. Yeah, proton mass, the front page of your reference tables, as well as charge of a proton is on the front page of the reference tables too. So both are given to you. Don't worry about memorizing those. Just know where to look, front page. And we end up with this 5.5 times 10 to the 12th meters per second squared for the acceleration. Oh, did I not? Hold on a second. I'm going to break this. Now I'll fix it. Okay, good. There it is. Okay. And the second part for the speed of a proton after a long period of time. This is where we can talk about electric potential energy. Hey, we kind of did that, right? Where we have Q delta V or QV, potential energy, electric-wise, turns into kinetic energy, 1/2 mv squared. Great, I can solve this. I can 1/2 times 2 divided by m, square root the whole thing, and I've got all this wonderful stuff like that. I may have kept it as a positive and just did the absolute value because it's not a huge deal. You're expecting 0 from that. And you end up 7.45 times 10 to the 5th. So here's a good example of another energy sort of thing where we did energy is Q times V and then convert it into 1/2 mv squared. So there is an energy just tucked along for fun. All right. That being said, let me give you last thoughts, final thoughts, and best wishes and such like that. So I think we're here, right? All right. So final tips for me for what could happen. There will be a time, there might be a time, let's hope that there won't, but there probably will be a time tomorrow where you get stuck on a question. And you've got really a couple options. We can either skip that question, we could guess randomly, or we can try to work through it. And depending on how much time you have left, and pace yourself on that, roughly 1 minute per multiple choice is on point. 2 minutes per FRQ middle point is pretty good too. But if you're stuck, number one, list what you know and what you're looking for. What is this question telling me? What is this question asking me to find? Skim through the reference tables real quick, just looking for symbols. I have E. What equation has E in it? I have Q. What equation has Q in it? Skim through there. Draw a diagram if it helps. It might not. I don't know. Visualization is an important thing. Take a deep breath. This one, probably more than anything else. Pause for a second. Take a breath. Clear your mind for 10 seconds, close your eyes, whatever it takes to calm you down, lower your heart rate, lower your stress, and then tackle it again. And trust yourself. You guys know a ton of these answers. And I think you know more than you think you know on there too. So work hard at it. You put in the time tonight. Go to bed. Get some good rest. Wake up in the morning. Eat a good breakfast. Carbs are great. But healthy breakfast, not sugar and, eat well. And then I would spend no more than an hour tomorrow looking over your notes, looking over these questions, thinking about the topics that you struggle with today or throughout the year. Go over those. But don't try to cram everything in. Don't. The day of the test is for, I really, really just need to remember this one concept. And then learn that one concept or focus on that one concept. Please don't try to cram all this in tomorrow. That's what tonight was for. But go do your best. Thanks for turning out for 5 hours or 10 hours for some of you. And good luck. You'll do great. You got this. Okay. Thank you, everybody. Again, if you have more questions or tomorrow want to chat or whatever, there is Discord. I know we're closing down that stream or that Discord channel when the exam starts. So whatever the set time for this exam is tomorrow, Discord's going to be shut down for it. But before that, please hop in, ask some questions, get some answers, and even just psych yourself up and get pumped up for this exam. All right. Have a great night, and thank you again for turning up. Take care.